Your turn.
అన్మ్యూట్ చేయాలా? Hello, madam.
Sir, shall
Uh,
I start, sir?
yeah, now it's 8:40. Yeah,
Uh,
we have.
okay, sir. Let
We'll,
start with
we'll,
our.
we'll wait. We'll wait. Hello. Ah.
Shall I start, sir?
Yeah, now it's 8:40. Yeah, we have.
Okay, sir. Let
We'll,
start with
we'll,
our.
we'll wait. I think we mentioned 50, right?
Yes, sir.
Wait. We have a. Sir, can I start recording? I can start right when madam will start, right? I can start the recording option. Sir. No, wait, madam.
Hmm.
I think we mentioned 50, right? Right. I'll mute my. Okay, this one. Sir, can I start recording? I can start right when. So I just muted YouTube so that I can take కొంచెం టైం తీసుకుంటుంది మేడం యూట్యూబ్ కి.
Hmm.
Okay. Uh, it's about 45. Okay, I guess.
Karatalu sir,
Ah,
let us start, sir. They will join in YouTube.
yes, yes, man. They will maybe, yeah. Okay.
Sir.
Yeah, we'll. Can I share that, madam?
No, sir.
No,
I
no.
uh,
The at least the first invitation one.
let us start, sir. నేను ప్రేయర్తో స్టార్ట్ చేస్తాను.
Okay.
Right. Let us start with prayer. सर्वे भवन्तु सुखिनः सर्वे सन्तु निरामया सर्वे भद्राणि पश्यन्तु मा कश्चित् दुःखभाग् भवेत् ॐ शान्ति शान्ति शान्तिः. Good morning to one and all. I, Dr. C.H. Kanchanalata, Assistant Professor of Physics, Indira Priyadarshini Government Degree College, Nampalli, Hyderabad. On behalf of today's Chief Patron, Sri Naveen Mittal, IAS, Commissioner of College Education, Telangana, our guest of honors, Dr. G. Adagiri, Joint Director, CCE Telangana, Dr. D. Rajender Singh, RJD, Office of Commissionerate of Education, Telangana, and Dynamic Academic Guidance Officer, Dr. Ganesham Garu, Principal, Dr. B. Srinivas Reddy Garu, Dr. D. Varalakshmi, GDC Indira Priyadarshini, Dr. P. Balabhaskar, BJR Government Degree College, Narayanguda, and respected faculty members, students, and participants from all over the world. The topic of today's international webinar is titled Recent Trends in Optoelectronics in Flat Land, Emerging Device Application on Two-Dimensional Semiconductors. We welcome today's resource person, Sir. Good morning, Dr. Nihar
Morning.
Pradhan, Assistant Professor, Jackson State University, Department of Physics and Chemistry, Jackson, United States of America. The objective of today's webinar: This year, 2020, because of pandemic situation, the entire education scenario has changed so much that this is the time for all students, parents, teachers, administrators, and policymakers to take an active part in making a meaningful outcome from a crisis situation. Students have to become more responsible and self directed. Teachers have to use both digital and physical classrooms, that is, a blended learning method, with equal excellence so that they can capture the attention of students and give them challenging assignments. And all these can be done with reference to the ideas given by Swami Vivekananda so that youth can be energized to become proactive in the field of science rather than passive learners as most of them today. So, coming to the title, advancement in technology leads to the discovery of many new engineering materials such as metallic glasses, nanophase materials, shape memory alloys, etc. Device application on two-dimensional semiconductors has provided a significant research by interacting with various other branches of science, creating impact on everyday life. Coming to electronic equipments, they are used in every aspect of modern life, from toys and home appliances to high power computer, and from space systems to process industries. The dependability of the electronic components of a system is a major factor in the work reliability of the system. Heat generation is an inescapable factor in all these systems. A dramatic increase in heat generation is due to continued miniaturization of electronic circuits with the result of high packing density. Hence, the temperature control is an important factor in running the electronic equipment. I believe the student community and participants will be benefited immensely from this webinar and hope they will develop a goal to excel in life and academics. I am very thankful and grateful to our principals and all the resource persons, namely Dr. Pradhan sir, Dr. Datta, who readily accepted our invitation and made this webinar a grand success. One instruction to all the participants: at the flag end of the session, kindly fill the feedback form and get your e-certificate. With this, I hand over the session to Dr. K. Parvatalu. Sir, please take over the session.
Thank you, madam. Thank you, Dr. Kanchalata, madam. Yeah, myself, Dr. Parvatalu Karakonda, Assistant Professor in Physics, GDC HYT, Usmania University. It's my immense pleasure to introduce Dr. Nihar Pradhan for this one-day international webinar. Dr. Nihar Pradhan is currently working as an assistant professor in Department of Physics at Jackson State University, Mississippi, USA. His current research explores optoelectronics properties, low temperature physics, magnetic properties of layered material and devices. Before joining as assistant professor in this university, he was working as a postdoctoral researcher at National High Magnetic Field Laboratory at Tallahassee, Florida. He completed his PhD in physics from Worcester Polytechnic Institute, Massachusetts, in the area of thermal conductivity of carbon nanotubes and composites. He is an associate editor of Emerging Material Journal in Springer Nature publication. His research supported by the NSF, National Science Foundation from United States. He published about 50 papers in international peer review journal, including Nanolator and ACS Nano. Today he is going to talk on optoelectronics in flatland emerging device application on 2D semiconductors. I believe that the faculty members throughout the state and the students will be benefited immensely from his presentation and hope that it will be enrich your knowledge. Without wasting of my time, now with this session, short introduction, I hand it over to Dr. Pradhan. Over to Pradhan. Thank you so much.
Thank you, Dr. Parvatalu. And thanks everyone for inviting me for this seminar. So let me share my screen.
Yeah,
right?
I'll just stop it, mine. Yeah.
Okay. Okay, can you see now?
Yes, sir. Yes.
Okay. All right. Thank you very much for this invitation, and thanks everyone for coming early probably today. So in this talk, I will discuss about very recent progress on 2D materials, particularly layered semiconductors, and how we can use these 2D semiconductor layered materials from single atomic layer to few atomic layers in many optoelectronic devices. So here is the here is the collaboration and generally performance sites. So we are at the Jackson, which is in Mississippi. It's here. And we have many collaborations. Throughout the collaboration, we are working on device fabrication and different measurements generally, which can't be possible at Jackson State University in our lab or in the university. So our main performance sites are at Jackson, and we heavily use many electronic devices, generally, particularly low temperature physics measurement at National High Magnetic Field Laboratory. These are the NSF sites, the National Science Foundations from United States government. So these are free to use, okay, any resources they have. Similarly, we are also heavily using Argonne National Laboratory. That's also Department of Energy facility here. And that's also free to use for any user. And with in addition to this, I have many collaboration with the RPI from New York, Howard University from Washington, and also the University of Houston at Texas. So my group currently working on, particularly the major part of my research is 2D materials, particularly layered semiconductor devices. We synthesize these layered semiconductor materials in one of the method which we will discuss a little bit later on. Then we fabricate the devices from single atomic layer to few atomic layer of devices. We studied the optoelectronic properties of these materials, many electronic properties and optical properties that we'll discuss probably. This is the main thing we will be discussing today. But in addition to that, we also look the low temperature physics, how these materials as a single atomic layer to few atomic layer form can go from metal to insulator phase transition at low temperature. And we are recently looking, this is the new funded projects from NSF. So we are looking also 2D and polymer composites, which is the dielectric materials. We are looking for high energy storage devices on these high dielectric materials. Okay, so starting from, let me acknowledge the people that they contributed on many of these work that I will be talking about. Priyanka is recently joined as a postdoc in our group. And there are many students, you can see many of them are here, undergraduate students. They were doing they did BSc or just probably they were doing, some of them are BSc physics, EC major, some of them are chemistry. Huan recently went to Stanford University, and these students they were currently working on. And there are also, you can see that these high school student also, they were working with me, and they contributed in many other works which we published, and eventually they were co-authors. So for the if someone is interested, I have a PhD position in my group, which is fully funded. Okay, but the requirement is BSc or MSc in chemistry. So if anyone interested, please contact me. So there are many other people they were involved in this research is from the Magnet Lab, Steve McGill and Luis Balikas. So Luis Balikas was my postdoc advisor, and there were many other people from Argonne National Lab and University of Houston and South Florida too. I have the collaboration and many things we are working on together. So initially, this is the outline of the talk. I will discuss a little bit about the 2D materials. What are those? How these materials develop. Okay. Then we will look a little bit synthesis routes, how these materials can be synthesized. And then mainly I will talk about the optoelectronic properties in this talk. Initially, like the electrical properties, where I will discuss about the how we can make the field effect transistor. Okay, that transistor we are using in many electronics components, including laptops and also your cell phones, etc. Everywhere. Okay, that we can see. So how we can develop a high efficiency transistor for this electronic devices that we can discuss here. Then at the end, I will discuss about the photovoltaics or the optical properties of these materials in single to few atomic layer form. Okay, let me start with one of the great speech, okay, that probably everyone know, R.P. Feynman. He is the physicist. And this is the talk he has given in 1959 at the American Physical Society conference. At that time, it was in 1959, it was in Caltech, okay? And at that time, there was no nanotechnology or anything about the nano. Probably it was kind of a dream that at that time, if someone talk about the nanostructure or nanotechnology, nanomaterials, and so on. And it was kind of a dream, and he thought about that, and he gave a talk that the plenty of room at the bottom. Okay, that was the talk. And at that time, he mentioned that if we can make the layer structure materials, okay, but the right layers below certain number of atomic structure or atomic layers, then the materials properties can change enormously, okay, compared to the bulk materials generally. And these materials with the right structure or single atomic layer form can be used many different ways, which we cannot use or apply the bulk materials. So if we can have a manipulation, okay, very nice niche manipulation of atomic structure, we can manipulate single atom, okay, inside the materials where we can keep them to make like a single atomic layer form of 2D sheets that we will be talking about, or one dimensional like a nanowire. Then these materials can give exceptionally different properties compared to the bulk materials. That's what he was talking about. And that was kind of a dream. And right now we are in that, the reality of that dream. We can manipulate the atoms, single atomic layer, single atoms inside the materials where you can put anywhere you want to make all these fascinating devices or the materials from single atom to like a two-dimensional form. Okay, so if we look, there is actually tremendous growth opportunities in electronics, particularly nanoelectronics. And this is one of the things, if we look that in 1956, this is the first hard drive, okay, IBM company, they made it. 5 megabyte is just like if you will take a cell phone photo, your own photo, then that will be 5 megabyte. And that photo can store in this IBM hard drive. okay? And you can see that how many people are pushing that to lift it, okay? So many people. So how heavy is that to just keep or store one photo, okay? That you can take by your cell phone right now. And that was in 1956. Now time passed by. You can have even 1 terabyte flash drive, okay? There are many terabytes you can put inside your pocket and roam around right now, okay? And these are very cheap, like 1 terabyte, which will cost like $10 to $13, and it's easier to use. And as we know that just recently, this is the Intel, Apple, who launched this iPhone Pro 11, okay? And this is the chip. You can see A13 chip they were using, okay? In the iPhone Pro 11, and you know, this chip is just 10 millimeter by 10 millimeter dimension. And in that 10 millimeter and 10 millimeter dimension, you can see how many transistors are there. 8.5 billion transistors inside these A13 chips. So this is possible because of the development of the nanotechnology. And this one, as per my knowledge, this is the 7 nanometer node of the transistor that they make, okay? And now the way, if you want to go down from 7 nanometer node to like a single atomic layer or 1 nanometer node, these transistors are made by MOSFET, silicon MOSFET, right? So you can't minimize the size of the silicon MOSFET down to single atomic layer. That won't exist, okay, so far. So then we can develop, or we can think about, if
Sir, you are muted. Radhan sir, you are muted.
Okay. Sorry.
No, I didn't mute, I think.
Oh, wait.
Can you listen up?
Wait, Niharji.
Yeah, I didn't see I muted here.
Okay. Oh, but these are, oh, now can you, yeah, I think it's fine. Yeah, go ahead.
Is it okay? Now you can hear?
Yeah.
All right, okay. So this is the iPhone Pro that I was talking about. We are using today, that within this 10 millimeter square, we have a 8.5 billion transistor, okay? If we want to go down, or want to make more and more transistor put inside these devices with this size or a decreasing size, you can't put 7 nanometer node transistor that we are using today. So you can look at different materials, probably a single atomic layer materials you can stack together, okay, one after another, and that will follow the Moore's law. Otherwise, Moore's law is going to end. Okay, so if we have such a high-tech electronics right now, okay, we can go like 8.5 billion transistor in 10 millimeter square devices, then do we need more electronics or more technology? Let's look that. If you look in your office room, let's see how many electronics you are using, okay? In our office, if you look, you might have a laptop, okay? You might have cell phone. Probably those are the 2 electronics, or maybe a TV, okay, in front of, or maybe few or light. Those are the few electronics you can see around your office. And there are many space, empty space, right? For example, table, that is not electronics. The roof is not electronics. The walls are not electronics. The books are not electronics. So there are plenty of room, okay, available to develop electronics which can fit to make a wall, electronic walls, electronic roof, electronic table, okay? So, but the silicon technology that we are using today does not fit there, okay? You cannot develop such kind of devices which can fit and use like a transparent electronics like wall or a roof, okay, or the tables. So there are enough rooms, actually more than like 95% objects, there is no electronics. Still we are looking for different materials which can fit there. So definitely we can look even like a transparent thin or flexible electronics, you can use like this, or you can use those electronics can be used for the like flexible electronic devices, some of these materials. And we are looking also at thinnest possible lightest materials for using the army. Okay, they can travel easily for long path without any heavy weight, so you can develop such kind of electronics with less weight materials. So one of the materials that people are looking nowadays is the layered materials. Okay, these materials you can make, this is the bulk materials that you can see, but once you make the layer, single atomic layer to few atomic layers, you can see that these materials are flexible. So you can have a flexible electronic devices. These materials are transparent in single to few atomic layer form. So you can make transparent electronics too. And if you can make these materials or synthesize or fabricate in large scale, then you can have a large scale electronic devices such as solar cell or in vehicle, aerospace, and so on. Okay, so why these 2D materials which we are talking about so interesting? Let's look at that. So one thing, initially we know 2D materials, it started from graphene, and when these are the two guys, great guys, Novoselov and Game, okay, from University of Manchester, they invented this graphene. Okay, not only invented, but they saw how interesting these graphenes are in electronic properties. Okay, so one of the interesting fact in graphene is you can see that this is the conduction band, blue, and this is the valence band, and there is no band gap. Okay, in this material, both the conduction band and the valence band, they touch together, which we call the Dirac point. Okay, there is no gap, so band gap is 0. So why this material, this graphene, is so interesting? Let's look that graphene has already measured that it has the highest charge carrier mobility in single atomic layer form. Okay, it is like 10 to the power 5 centimeter square per volt second is the mobility at a room temperature that you can even use today. So why this is, such a high mobility it gives in a single atomic layer form? If you look the energy, okay, in non-relativistic case or relativistic case, that you can see that this is the energy, which is the mc square over square plus cp whole square, where c is the velocity of light, p is the momentum, m is the mass. Now if you look, this is the total energy, okay, of the particles. Now in non-relativistic case, where the charge carrier can move very less compared to the low velocity compared to the light, okay, then in this case you can expand this energy or term like this. Okay, so now if you look at that, in V is very, very less than C in this condition, if you plot the energy as a function of P is the momentum, okay, of the charged particles, then when P is equal to 0, okay, there is E is equal to mc square. So energy is not equal to 0. Okay, so you can see the energy and momentum relation like this parabolic form. Now if you look at that, if the mass of the particle, let's say mass of the charged particle is 0, okay, so if m is equal to 0 here, now you can see E is equal to Cp, right? So this first term will go away, and this will be Cp square root over, which is the E is equal to total energy is C times P. P is the momentum, C is the velocity of light. Now the velocity, if you take that, okay, derivative, then the velocity of the charged particle is approximately equal to velocity of the light. Now if you look at this, energy is equal to Cp, and if you draw that energy versus momentum, this is the E is proportional to P, so you can get this diagram, right? And this is the diagram you can see here. This is the linear dispersion of band structure, okay? And this is same linear dispersion we got here. At what condition? When the charge particle is zero, mass of the charge particle is zero. So graphene, what happened is, graphene shows extremely high charge carrier mobility. That means the electron can move inside the single atomic layer graphene like a light, compared to like a light velocity. Okay, why? Because of this linear band dispersion, where the mass of the charge particle is like a zero. Okay, there is no mass. That's what we got from here. Massless charge particle, we call massless Dirac fermion. Okay, if you know the Dirac equation and so on, then it is easier to follow. But these are very, I mean, nice relativistic formula where you can understand very easily how this happens in graphene. So if we look the mobility of the electron in graphene, which is like 10 to the power 5 centimeters square per volt second, but we are using silicon MOSFET everywhere in our cell phone, any electronic devices, for example, computer, TV, everywhere. So if we have a graphene with such a high mobility, then why you are using silicon MOSFET still everywhere in electronics? If you use the graphene, okay, then there is no band, band gap. So always there are electrons at, at room temperature, there is always electrons can go from valence band to conduction band. So if you use this graphene as the transistor in your mobile, for example, then you can switch off the mobile when you don't want to use it, but the mobile can still drag the charge from your battery. It will not switch off, okay? Because there is no band gap on this material, so electron can easily always available in conduction band, and they can drag or suck the battery, okay, any charge from the battery. So these are not good for the field effect transistor devices, even though it has extremely high charge carrier mobility. So we do have many other materials in single atomic layer form to few atomic layer form. They have sizable band gap, okay? So you don't need to worry about whenever you want to switch off the transistor, it will be switch off, completely switch off, okay? And those are actually flexible and transparent too. So you can use many different applications as the thinnest possible field effect transistor. So here you can see some of the materials, okay, but there are many materials now, probably several thousands, okay, layered materials. Many of them are like a semiconductor. These are the semiconductor, okay, and some of them are semi-metallic also, and some of them are insulator like hexagonal boron nitride. Many, some of them are, few of them are superconductors so far we know in a single atomic layer form. And recently there are few elements also, materials, layer materials developed. They are semi-metal and magnetic too, okay, ferromagnetic. So we need many different type of application if we'll work and find out how they work. So let's look at how these 2D semiconductor, when we are talking about single atomic layer form, okay, how they looks like. So this is one of the, this is the one atomic layer. When we call the one atomic layer of MOS2, molybdenum disulfide, or similar semiconductor, okay, this looks like this. So one atomic layer means three, this is 3 atomic layer structure. And if you look the MOS2, molybdenum disulfide, molybdenum is in between, okay, these are the black dots, sulfur and sulfur are on the top, okay, and bottom. So molybdenum atom is sandwiched between 2 sulfur layer. And in a single atomic layer structure, they have strong in-plane covalent bond. So if you buckle, okay, bend them, it will not, you cannot break it. They have strong covalent bond along the plane. Now, if we look the 2 atomic layers, you see they didn't touch because they have the covalent. This is not covalent. These are the van der Waals weak attractive force, okay, from one layer to the another layer. So it's easier to make them separate, okay. How you can use, I will show you how to use this or make it single atomic layer form from the bulk materials, okay. So this is how the structure looks like, but how these materials changes the electronic or optical properties when we go from bulk to single atomic layer form. Let's look that. So here is the band structure. Okay, band structure will tell about how the electronic structure looks like, how these materials can be used as a semiconductor or semi-metal, or how we can look or apply this. So this is the band structure of MOS2, molybdenum disulfide, and this is the bulk crystal band structure. If we look at that, this is the conduction band, this is the valence band, and they were separated by 1.3 electron volt. Okay, this is called band gap or energy gap between the conduction and valence band. And now if we look that, top of the valence band is somewhere here, bottom of the conduction band is somewhere here. So if the electron will hop from valence band to the conduction band, it won't go directly, okay? It has to bend. It has to bend to go to the conduction band minimum, but it goes directly up, then falls, okay? We'll talk about that. And this is the bulk band structure of MOS2, how it looks like, which is 1.3 electron volt band gap. When you make it thinner and thinner, you make it thinner and thinner. So 4 atomic layer, you can see the band structure pretty much looks like a bulk, okay? But there is a, change in energy gap or band gap here. When you go to the 2 atomic layer, okay, this looks like this. And when you reach to 1 atomic layer, you can see that there is a huge difference from bulk to single atomic layer band structure. The top of the valence band is exactly underneath of the bottom of the conduction band, okay? So this is called direct band gap materials, and this one is called indirect band gap materials. In direct band gap materials, electron can hop directly from the top of the valence band to the bottom of the conduction band, okay? So then if the electron will lose that energy, then that can emit, okay? And that we can see as a photoluminescence also, and it can come back. So this is the materials. There are several materials like MOS2. This is for example, but there are tons of materials now. They go from indirect band gap transition to the direct band gap, okay, electronic transition, when you make them bulk to single atomic layer form, or you can say indirect band gap to direct band gap of these materials. And not only that, the band gap, nature of the band gap changes. The energy gap also increase. You can see that this is in the bulk, the band gap is 1.3 electron volt. When you make 1 layer or single atomic layer, the band gap is 1.9 electron volt. Okay, so band gap is increasing. So how it is increasing? We understand that very well, and you guys know also, if those people who took the quantum mechanics, okay, particle in a box problem, when you solve the quantum mechanics particle in a box or the rectangular potential well, okay, you will come across that energy, okay, total energy is equal to n square h square over 8 ml square. L is the length of the box. Now, if the length of the box decrease, okay, smaller and smaller, what will happen? Energy will increase. That's what it is happening. When you go from bulk, bigger size, to small size, single atomic layer form, it just the energy is increases. Okay, that's called quantum confinement effect. Okay, in nanoscale materials. And this is the photoluminescence. You can see if you measure the photoluminescence of single atomic layer of MOS2, which can use as a light emitting diode, okay, then you can see that single atomic layer shows huge photoluminescence peak. Photoluminescence means you can excite the electron from valence band to the conduction band, then that electrons will emit the light. That's what you have to catch it, okay? You can measure, sense it. That's called the photoluminescence, when the electron will jump from the conduction band to valence band. And if we look and compare the photoluminescence to two atomic layer of these materials, you see. There is photoluminescence in 2 layer, but compared to 1 atom layer, it is 0, okay, or so small, because this is the direct band gap material, 2 layer is the indirect band gap material. So there is a lot of, optoelectronic application that you can use, or have these materials, and you can fabricate and apply in many different types of optical devices. Okay, so let me show you how these materials you can grow in lab. Okay, there are many different technique. Okay, you can do the thermal evaporation and many different way, but 2 important method people are looking or using now is, one of them is chemical vapor deposition method. You can use this chemical vapor deposition method, and you can make a single atomic layer, bi-layer, or 3 layer, depending upon different temperature, different pressure, different condition of the chamber. Okay, you can grow them in larger scale. You can see that this is like a approximately 1 centimeter square. We got that. Okay, this is developed, grown in Penn State University, and you can see that this is the triangular plate, which is like around 50 micron, okay, on the silicon dioxide substrate. Not only you can grow a single, semiconductor materials like MOS2 here, this is the tungsten disulfide, but you can grow actually one after another, like a heterostructure. You can see here in 3rd figure, these are the heterostructure of MOS2 and WS2. You can start from MOS2, grow that, then after few minutes or few hours, you can stop that, then start the tungsten disulfide. Then tungsten disulfide will start growing, okay, laterally connected with MOS2. Then you can, do repeatedly different materials to have different heterostructure. Okay, so there is another method which generally I use in my lab, is the chemical vapor transport method. So this method will provide you to make the bulk single crystal, okay, not the single atomic layer like CVD ground that we talked about before. So in this case, but this method is very simple. If you are using, let's say you are growing MOS2, you can buy molybdenum powder, you can buy sulfur, you mix together, then you can use some other agents which can process the reaction, okay, like chlorine, bromine, iodine, okay. That will not react there, but it can process the reaction inside the chamber. Then you can raise the temperature, like up to depend upon different materials, it can melt. Then when you cool down, they will form nice crystal, okay. And you can see that very nice single crystal, like even more than 1 centimeter size of this single crystal you can grow. And this is the TM image. You can see the single atom structure also without so much defect. Okay, there are defects, of course, but in a small scale, you cannot see that many defects here. And this is the method we are using, which is not the good method to make like a, if you want to use like industrial scale of the devices, then you cannot use the Scotch tape method. Okay, so here is one of the high school student. You can see Jason. What he does is he can take the Scotch tape, okay, put the materials, then just exfoliate, okay, using the Scotch tape many times. Once you exfoliate, these are the layer materials, and they were like a van der Waals forces between each layer. So you can peel them apart very easily, and then you can transport onto any surface you want, okay, like silicon oxide surface, any other surface. So this Scotch tape method, okay, this is not the, the good method if you want to fabricate the devices in large scale, okay, you can't do that. But is there any alternative route to make this bulk single crystal to like an industrial scale of device fabrication? Yes, there are many other techniques. You can make this, from this bulk single crystal, you can use a particular solvent and mix them well, okay, and you can form a 2D ink. then you can use the printing. Okay, nowadays 2D printing is available. Okay, very nicely you can print it in many different electronic devices. Okay, so how you can make this single atomic layer to few atomic layer of these materials in electronic devices. One of the device that we'll be talking about is the field effect transistor. Okay, so what is the transistor means? So a transistor, this is the schematic of a transistor, and a transistor means 3 terminal devices. Okay, that's why it is called transistor. Okay, so in transistor, these are the 3 terminal. One is the drain, another is the source. So you can apply the drain source voltage so that electron can move from source to drain. Okay, that's what you measure. Then the 3rd terminal is called gate. Okay, you can apply the gate voltage, okay, which is on the top of, there is a gate dielectric you can quote. Then you put this gate electrode. When you apply the gate electrode, you can accumulate how many charge carrier you want. Let's, for example, we'll discuss that. So this will control the charge carrier inside the channel or inside your field effect transistor. When you want to switch off your transistor, it will be switch off. Okay, it will not drag any charge or any current from your battery. So that's what it does. The transistor will be on or off. So this is one of the transistor. You can see that on silicon dioxide substrate, this is the single atomic layer field effect transistor. When you see that in of course in silicon dioxide, there will be a fringe pattern and there will be reflection. That's what you can see it. But if we will take this transistor on a glass substrate somewhere, okay, it is completely transparent. You cannot see it. These are like a very less, light can absorb with these materials. So these are like a transparent and flexible. You can make it, buckle them, anything you want. So another important parameter in field effect transistor, what we are looking is high charge carrier mobility. So what is the mobility means? Mobility means how fast the charge carrier can move inside the channel. So higher mobility is the better for electronic devices, right? So how we can get, we talk about, if you know the semiconductor physics a little bit, then we everywhere in electronic circuit, we use MOSFET, we call, okay, silicon MOSFET, but there are like a P-type or where the electrons are more, and there is another called the N-type where N-type is the electrons majority or electrons are there, and P-type means where the holes, okay, positive charge carriers are there. So how we can make these materials as a P-type or field effect transistor or N-type field effect transistor. Let's say this is one of the transistor here, okay, this is the semiconducting materials, single atomic layer to few atomic layer, and this is the fabricated on the silicon dioxide substrate. Silicon means it is the highly doped. So this is the conducting, and they were separated by a gate dielectric. Gate dielectric means it is the insulator. Okay. So when you apply the gate voltage, this is the source and drain. If you apply the voltage on source and drain, which is called drain source voltage, then the carrier will move from source to drain. Okay, but how many carrier are there? Only that number of carrier will move. So how we can control the number of carrier in the channel? That's why the gate is there. Okay, you apply the gate voltage. If you apply the gate here, negative gate voltage, then this is the electron. Negative means this is the electron you can inject here or accumulate. The opposite side, because you are applying gate voltage from here to the source. Okay, so this is like a capacitor. So opposite end of the capacitor will be accumulated by the holes, opposite carrier. Okay, if this is the electron, this is the hole. So when you apply the drain source voltage, these holes will move across the channel. So this looks like, if you measure this as a field effect transistor, it looks like this. So when you apply the more and more negative voltage, okay, if your material has sufficient holes, okay, inside this channel, then you will get more and more current. So at a certain voltage, your transistor will on. So this is the on state of the transistor. This is the off state of this transistor. When you don't work, okay, transistor generally off, switch off. When you work, okay, with, I mean, the transistor will work, transistor will be on in this state. So the opposite one is, if you now change from negative gate voltage to the positive one, then you can induce electron inside the channel, okay, and the corresponding field effect transistor will look like this. So at positive gate voltage, you will see the transistor will be on. At negative gate voltage, transistor will be off. So this is called the typical N-type field effect transistor, where electrons can conduct. Okay, there are some materials, okay, currently in silicon MOSFET that all we are using today in everywhere, okay, electronics. These kind of like a silicon we dope the silicon with something, okay, like a boron, phosphorus, and so on, to have N-type, to have P-type. We connect them together, so we have ambipolar, which is called ambipolar device. That's what you need, okay, in many MOSFET, okay, devices. So if you have a like if your channel has both electron and holes, then you can sweep from negative to positive. You will see there is a N-type part field effect transistor, and there is also P-type field effect transistor, where holes can be conduct, and this side the electrons can be conduct. Okay, so let's look at how these kind of effects we can get from this single atomic layer to few atomic layer of these 2D materials. So this is the first one of the, I mean, first field effect transistor, okay, it published with MOS2, single atomic layer MOS2 field effect transistor. And you can see that in the schematic, this is source drain, there is a top gate, okay, you can apply also back gate here underneath, so you can have like a dual gate also. The top gate will be accompanied with a hafnium dioxide dielectric here, okay, but you can use many different dielectric. And you can see here, this is the typical N-type field effect transistor, where transistor is off in negative gate voltage and on in positive gate voltage. So this is the N-type field effect transistor, or we call that electrons are the majority charge carrier. If you look that in logarithmic plot, this is the logarithmic plot, this is the linear plot, then you can see how quickly the transistor will switch on from off state. This is the off state and this is the on. Okay, quickly it switch on. And how much voltage it needed? 74 millivolt. It needed, okay, this switching voltage is 74. That is called sub-threshold swing. And smaller is better. Okay, people are now actually, they already got the less than theoretical limit. Theoretical limit of this sub-threshold swing is 60 millivolt per decade. But people already observe on this material even 30 millivolt per decade. One of the important part, okay, in this semiconductor devices, you have to measure the mobility, okay, how fast the charge carrier can move inside the semiconductor material, single atomic layer form. So in a single atomic layer, you can get like in MOS2 15 centimeter square per volt second to like a 50 centimeter square per volt second, but not much, okay. We'll discuss about that, why it is not much. But if we increase the number of layer on this molybdenum disulfide field effect transistor, let's say you increase from single atomic layer to 10 atomic layer, okay, you can see here that we discuss, I mean, we fabricated, and there are many contacts, okay, don't forget about the many contacts, but you can use 2 terminal or 4 terminal and so on. So we use 2 terminal, you can apply the current and voltage, okay, and measure apply the voltage, measure the current in the same contact, 2 contact. And you can see that when we increase the number of layers from single layer to 10 atomic layers, the mobility increases. Okay, this is still typical N-type field effect transistor, but mobility increases to close to 100 centimeters square per volt second. So this is kind of like a 80 to 90 times higher than single atomic layer field effect transistor. Okay, so the question here is like, if you want to use for semiconductor devices, maybe single atomic layer of MOS2 is not that great, but if you want to use 10 atomic layer or like probably 10 to 15 layers, the mobility is good, okay, higher. Now, why these mobility are low? One of the things that we look at, the effect of contact resistance. So those people who were measuring, okay, the traditional method, this is the traditional method we use to apply, measure the IV curve, particularly apply the voltage, measure the current. So because these are the two-dimensional materials, when you put a contact, okay, on these materials, the contacts are not good at all, okay. So the metal contacts which touch to the semiconductor, there is a huge contact resistance, or we call the Schottky barrier effect, okay. They were not alloyed very well. So the electron which flow from the semiconductor to the metal, they suffer there because of the resistance associated in the contact between the metal and the semiconductor. So what you can do is you can measure, instead of this 2-terminal, okay, IV curve, you can measure in 4-terminal. So what is 4-terminal? You measure the current, okay, in separate 2-terminal, outer terminal, but sense the voltage in between, okay, separately. So what it will happen is, I'm not going to discuss briefly, but this is called the 4-terminal measurement or Kelvin probe measurement, if you heard about that, where the contact resistance can be reduced, okay. The contacts, when you apply the current and measure the voltage in same terminal, the contacts will hit, okay, together because of the heat generated between them. But when you sense the voltage and measure the current separately, then contacts are no more hitting because your voltage sensing is different, current measurement is different, okay. So if that case, from the same device you can see how much the current, you can see how much we improved, okay, and the mobility is like a 3 times compared to 2-terminal. So probably we understand that the contact resistance is one of the major issue in 2D semiconductor to make the intrinsic materials, measure the intrinsic electrical properties. So I'm going a little bit, I will go faster here. These are the another type of devices. This is tungsten diselenide. You can see that all these materials are grown in chemical vapor transport method, okay. When you measure the tungsten diselenide, this is no more N-type, okay. This field effect transistor shows like a P-type behavior. As you can see, the transistor is switched on in negative gate voltage, not the positive gate voltage. Positive gate voltage is switched off. So this is the typical P-type or hole doped semiconductor. And for like you see the single atomic layer or 2 to 3 atomic layer, we measured here, the mobility is almost 300 centimeters square per volt second. And this is the 2-terminal measurement, by the way. And when there is called the Hall effect measurement, if you know, these are the trusted, measurement method that people do, the those people who are working on the transport measurement, they care about, okay. You apply the magnetic field, charge will, you apply the current here, then charge will deflect perpendicular to the magnetic field and the current. That's we know by Hall effect measurement, okay. And then we can measure that resistance or the Hall resistance. You calculate the field effect, the mobility from Hall effect measurement. When you calculated that, you can see that these materials can give whole mobility of this material is 670 centimeters square per volt second. And this is like an intrinsic charge carrier mobility. At room temperature, we calculated around 500. And those people who, working on silicon MOSFET, that silicon MOSFET we are using today in all the like electronic devices, the whole, okay, P-type whole mobility of silicon MOSFET is 500. So this is kind of a material which is like a single atomic layer form, okay, can probably, it is, we are very far from replacing silicon technology, by the way, but there is a chance, there is a hope, okay. These materials can be used or replace silicon technology that we are using today if we improve the charge carrier mobility, stability, and so on. Okay, so I'm going to show you another field effect transistor here. This one is the MoSe2, molybdenum diselenide, and this one is called ReSe2, called rhenium diselenide. Okay, these are these materials are grown in same condition like MOS2, tungsten diselenide, and so on. But you see, it is the purity you will get in the crystal. Okay, these materials show like a p-type field effect transistor in negative gate voltage, as well as n-type field effect transistor from the same material. So now currently in silicon MOSFET that we are looking at, complementary logic we call, where we have a electron and hole p-type and n-type transistor both together. Okay, we are using now. They were made differently, then they joined together. But this is the material, you don't need to do anything, any doping. So this kind of intrinsic characteristic that you can get if your crystal, you can grow a nice crystal which is both hole and electrons are there, and you can use for the complementary logics. Okay, we also, I mean, tested for a, this is one of this phase shift modulator. Okay, we look where we are using actually this phase shift key or the modulator can be used for radio station. If you are using a radio station and I mean tuning from one station to another, you need phase shift key. Okay, so there are many other technology like gates. Okay, logic gates. You can use NOR gates, AND gates, okay, AND gates, and so on can be used from these ambipolar devices. Okay, this is one of the gates. Okay, that how the design looks like in a single atomic or few atomic layer form. And this is the NOT gate, and this is the NOR gate. You can put together to make AND and so on. Okay, so these are, I mean, with the development. Okay, now you can see that. Let me tell you about the silicon MOSFET. The silicon MOSFET that we are using everywhere, the N-type field effect transistor and P-type. P-type mobility in silicon MOSFET is around 500 at room temperature. Okay, and N-type mobility or N-type field effect transistor that we are using is around 1500 centimeters square per volt second. Okay, now you will see here few atomic layer of indium selenide that people develop. Okay, you see the room temperature mobility here is around 3000 already. Okay, which surpassed the silicon MOSFET event, around 3000 centimeters square per volt second. Forget about the low temperature. If we are using at a room temperature, this is one of the best material. Indium selenide has the potential to replace the silicon MOSFET. There is another material called black phosphorus that people are looking now currently. Okay, and this is the one of the article that you can see that the room temperature hall mobility. Okay, they reported around probably 4000. Okay, this is 10 to the power 4, so around 4000 or 4500 centimeters square per volt second. Okay, in black phosphorus. But black phosphorus is very difficult to use for the electronic devices because it degrades quickly at room temperature. You put the black phosphorus in few atomic layer form, within an hour it will degrade completely. Okay, so but people are looking for how you can encapsulate it. Okay, and preserve the intrinsic nature, pristine nature of these materials for the optoelectronics properties. Okay, there are many challenges, of course. Okay, measuring the intrinsic properties, that is one of the big challenge that people are looking how you can improve. Okay, the materials property, or probably materials are good, we don't know how to measure it okay, nicely to get the intrinsic properties. So there are many challenges. You can see that in this picture there are many I mean electron phonon scattering. Okay, that limits the charge carrier mobility. There are Coulomb impurity scattering. When you fabricate the devices on silicon dioxide substrate, there are many impurities underneath. Okay, that will act like a scatter. Okay, when the charge carrier will move, that also limits the charge carrier mobility, surface phonon, surface roughness, structural defects. Okay, whatever it is there, and we discussed the contact resistance. Okay, these are many different things that limits the charge carrier mobility in this 2D semiconductor. If we can minimize, okay, people are looking at these things, okay, for example, contact resistance that we discussed about, but all these things can be minimized so that we can improve the charge carrier mobility of the devices to apply in many optoelectronic devices that we are using today. Okay, so I'm not going to discuss, but I'm going to show this thing that in this probably last 2 years, 2 to 3 years, or probably in this 2D materials, okay, two great, okay, discovery has been done. One thing is the Hofstadter butterfly effect. So what is this means is, if you are measuring the electronic, conduction or the charge carrier, how it moves in high magnetic field, okay, then in a nice two-dimensional materials, okay, then the magnetic flux and the energy, okay, levels that you will measure in this nice two-dimensional crystal, high mobility crystals, then you will see this is the magnetic flux energy diagram. And this was invented by Professor Douglas Hofstadter, okay, long back, you see 1976 in his PhD. And this is discovered by theoretically, he discovered. But after that, what happened is nobody able to measure that or verify experimentally, because we do not have such kind of nice crystal in two-dimensional form which will show very high mobility. But once the graphene discovered, okay, after 40 years, nearly 40 years, first time that Columbia University, okay, people, they discovered this Hofstadter butterfly effect, okay, experimentally. So it looks, it calls butterfly effect because it looks like a butterfly, okay, when you put it in color form. That's why it is called butterfly. But how the charge carrier move in magnetic field at low temperature, that's what the magnetic flux and the energy, which is called Venn diagram, okay, it looks like. So this is one of the great discovery in two-dimensional material. So recently, okay, last year, 2019, MIT and Columbia University, first actually discovered by MIT groups, they look that if you have a single layer graphene, okay, graphene is semi-metal, there is no band gap, okay, if you measure the electrical conductivity, it is just like a metal. But when you put another graphene, okay, 2 layers of graphene, 1 layer and put another 2 layer graphene, that will be also, if you take the 2-layer graphene and measure the conductivity, that is also like a metal, okay, because single atomic layer is metallic. But if you have a 1 layer and top, you can put manually second layer on the top of first layer, but the second layer is not exactly the way first layer is. So if the second layer will rotate very slightly, you can see 1 to 1.27 degree precisely, very precisely, and measure the electrical conductivity. You see these 2-layer graphene with angle between them 1 to 1.27 degree. They were not metallic, they were superconductor. Okay, so this is one of the like a great discovery that into this two-dimensional material. This is not the semiconductor, but this is nice, okay, to look in low temperature physics. Okay, so let me go quickly to, okay, how much time I have, Parvatalu?
Another 30 minutes.
All right, okay, I think I have,
yeah.
Okay, I have enough time. Okay, so far we discussed the electrical properties, how you can develop nice field effect transistor. You can use in many optoelectronic devices such as transistor. Okay, we discussed that. We discussed N-type field effect transistor, P-type field effect transistor, MOSFET kind of like a ambipolar field effect transistor, and so on. So now we'll discuss that how good these materials, since these are the semiconductor, many of them, how good they are with respect to when you shine the light. Okay, these materials shows very interesting optoelectronics properties and strong light matter interaction between them. When you shine the light, there is like a tremendous electron and hole pair it can, generate by absorbing a tiny amount of light. Okay, this material does not absorb in a single to few atomic layer form. It does not absorb that much light, but it can produce enormous electron hole pairs because of strong light matter interaction. So why these these materials show very strong light matter interaction? So this is one of the theoretical electron density of state calculation, how many electrons are there, okay, in density of states, okay, in calculation for these three different materials. And in density of states, as a function of energy, you can see there is a spiky thing, okay, it's coming from. And that spiky, which is called actually called Van Hoff singularity, okay, those people who are looking theoretically probably know that. And this Van Hoff singularity comes from the chalcogen atoms, p orbitals, and the transition metals, okay, atoms. So these are like electronic wave functions, okay, overlapping nature of these two, electronic wave function from transition metals and the chalcogen atoms. And that gives you the spiky field, the spiky nature of the density of states. And those are responsible, okay, for strong light matter interaction on these materials. The other materials which does not show like this spiky behavior. So let's look at that. How why these materials are so interesting, okay? Is these materials better in optical devices than the silicon or any other materials that we are using today? Let's look. One of the thing is the photodetector. We use photodetector probably everywhere, many optoelectronics devices, okay? We use imaging, optical communication, safety, security, environmental sensing, defense, IR detection, and so on. Everywhere, even you can use in your remote control that you are using, okay? So for all these cases, we need high sensitive materials or devices, fast response time, and we need thinner also, right? Which also we need low noise and long lifetime, of course, and also the cost should be less. So let's look that these are the, if you go to the market and find or purchase the photodetector, these are some of the photodetector available in the market, okay, small to larger. And these are the response, how these devices, silicon MOSFET, okay, this is silicon photodetector, how they respond to the light. You can see here 300 nanometer whole UV to like a IR region, okay. And you can see the responsivity. Responsivity means the photo generated current divided by how much optical power you shine on the materials, okay, that is called the responsivity. So if you have a less power and more current you are generated, photocurrent it is called, then your material is highly response, okay, sensitive is more. So the responsivity you can see less than 1 ampere per watt on the silicon photodetector we are looking for, okay. And the photocurrent that you can measure is the, you shine the light, measure the current, and don't shine the light on the material, measure the current, that is called dark current. And if you will subtract that, that is called photocurrent, okay. Now let's look at the single to few atomic layer of this photodetector, okay. One of the example is tungsten diselenide photodetector. So when you measure that on a, just this is the 3 atomic layer or 4 atomic layer of the device, tungsten diselenide photodetector, and this is the off current. You started measuring current, and suddenly you switch on the shining light on the top, okay. We use your 532 nanometer from the laser, and it immediately, okay, switch on this phototransistor. And then we switch off here, it immediately goes to 0, okay. So quickly it responds. So how quickly it responds? You see that from off to on, time is 40 microsecond. Okay, so fast, this one. Okay, similarly, this off also switching from on to off. Now let's calculate the responsivity, okay, by measuring this. This is the responsivity. We use actually 4 terminal and 2 terminal, all this, measurement that we talked about. And you can see that the responsivity in a small power of the laser, okay, here, probably 250 nanowatt of the laser power, your responsivity is 85, nearly 100 ampere per watt. And the silicon photodetector that we discussed, that how much responsivity, this is just 0.6 in 532. Let's look the 532. 532 is around 0.4 amp per watt. And here, these are the materials which are transparent, flexible, okay, materials, and the responsivity for the photodetector is around like 1,000, probably 100 times higher than the silicon photodetector we are using today. You can have the external quantum efficiency. This means that when you shine the light on this material, you generate the electron hole pair, right? The materials will absorb the light, electron and hole pair will get excited, okay, and they will be separated. So number of electron and hole pair that you measure, okay, in this case, divide by number of incident photon. If we will divide it with that, that will give you the quantum efficiency of these materials, and that is around, let me see here, it's around like a 20,000%. So probably some of you probably looking at how this materials is, we heard about 100% quantum efficiency. 100% means how many photons it absorbs, exactly same number of electron hole pairs you can measure. That's called 100% efficient, right? But this is 20,000% that we probably never heard about, okay? That's theoretically not possible, kind of. So let me tell about why it is 20,000%, okay? So these materials in two-dimensional form, okay, there are many defects, or maybe the underneath there are many shallow area, okay. So in the defect sides, when the electron hole pair will generate, one of the charge carrier, probably the minority one, okay, one of the charge carrier will get trapped in the defect side. So the other charge carrier, let's say hole is trapped, then the electron will find another hole to recombine, right? So till that, it can circulate many times, okay, with your external circuit that you are measuring the charge carrier or the current, okay? So it can probably circulate many times before it find another hole, okay, to recombine. So that's why even though one photon, okay, one electron pair it generates, it acts like many hundreds of, because of this trapping nature, okay? That's why the efficiency is so high in this material. So which is probably very interesting. So the last part I will talk about in this material is the solar cell application, okay? So these are the semiconductor, and these are nice band, band gap from visible region to like a far infrared region. Also you can get small band gap of these materials. So how the PN junction works? So if someone took the semiconductor physics, this is the N-type material and we have a P-type material. Once you combine them together, okay, N-type and P-type, then when you combine them, you can see that this is the electron side, this is the hole side, means positive charge carrier, this is the negative charge carrier. When you combine them, what will happen is in the vicinity or in the junction region, some electron will go through to the positive side, hole side, okay, that you can see here. And there are some holes will go to the electron side, and you can see the holes here. So they form the electrical barrier kind, okay. Here, they develop the potential in this small region of the junction, which is called the p-n junction. One is the p is the holes, n is the electrons. Now this is the positive charge carrier, negative charge carrier. Now these holes cannot go here, okay, just freely, because they will see they can cross the electron side, but they will see a barrier of holes. These holes, positive charge carrier will repel these holes if they will try to enter, okay, because of this develop the electric field in this p-n junction area. Now if we apply the apply the voltage, okay, in this case, so what will happen is, if you are applying the positive terminal connected to the positive sides and the negative terminal connected to the negative side. Since this is negative cannot be, this terminal cannot be attracted the electron, because electron will push away in this case, okay. But when they will push away, what will happen is you won't see, or the electron will not be attracted in this case to the negative terminal. So you won't see. Similarly here, the holes cannot be attracted to the positive terminal, right? So you won't see any current in this case. So you will get a zero current. That is called reverse bias, okay, in p-n junction. Now, if you change this terminal, okay, positive and negative, you change that. You put the positive this side to the electron, negative to the holes. Then what will happen? The positive will go this side, the negative, the positive hole charge carrier will go to the negative terminal, and the electron will flow to the positive, okay. And you can see the current which will increase, okay. That is in nonlinear behavior, that is called the forward bias of the p-n junction. So one side there is no, which is the reverse bias, there is no current. Other side there is a huge current, okay. That is called rectifying behavior, or we call the rectifier also in p-n junction. Now if you shine the light in this case, let's shine the light, okay. Don't apply the voltage in that we did here, okay, like a diode behavior. You shine the light, what will happen is you can generate in this material so many electron and hole pairs by incident photons, okay, from the light signal. There are many electrons and hole pair. You don't need to apply any voltage externally. And these electron and hole pair, if will combine with a wire externally, the current will flow and you will get the current. Okay, that is the basics of this photovoltaic solar cell, or p-n junction photovoltaic solar cell, or silicon photovoltaic module that we are using today. So I will talk about here the little bit solar cells in 2D materials. So in this case, since these are planar structure, okay, there are so much actually you can do in this case. This is very early stage working on solar cell based on 2D semiconductor. Very less study has been done. So in this case, you can see lateral p-n junction you can develop. There is a n-type material, p-type material. You combine them together laterally, they will form p-n junction. Okay. In another case, it is a vertical p-n junction. You put n-type material here, put on the top a p-type materials. Okay, it is called vertical p-n junction. When you shine the light, there are lot of electron hole pairs it will generate between these two overlapping region. Okay, and there is another p-n junction. In this case, you see one of the thing is even the junction area is here. Once the electron hole pair will generate, the electron will move here laterally, okay, and holes will move also laterally. But when they move laterally, actually you can't catch. They suffer with a lot of kind of like a scattering phenomena and so on. So the efficiency in this vertical p-n junction in this structure will be less. Now you can look at vertical heterostructure, but you put the metal contact top and down so that whatever the junction area, okay, the electron and hole pairs will, form or generate, you can directly catch them if your electrode is on the top, okay? So they will not flow laterally. They will not move laterally. They will be directly collected on the top on the electrode. And probably that will be the best way to fabricate the PN junction devices based on this material. So I will show you one example. There are many things in this case, but very less work has been done so far. Okay, you can see in the literature. But this is one of the photovoltaic PN junction we call electrostatic PN junction. Okay, because you apply the electric field and form the PN junction. So how this device looks like? You can see here, this is the silicon, okay? Silicon dioxide, this is the dielectric layer. You put two gate means metal electrode. Gate 1 and gate 2, that is the metal electrodes. Then you put the BN, BN is the boron nitride, which is a dielectric material. Then you have your own semiconductor material, in this case MOSE2, okay? Then these are the source and drain. Okay, 2 metal contacts. You don't need 4 metal contacts here. It's enough. So when you apply the gate voltage, this is the gate 1 and gate 2. There are 2 gates. They were separated. You see, they were separated just few hundred nanometer apart. Okay. So when you apply the gate voltage, let's say positive here in gate 1, you are generating electron. Okay, because when you apply the positive gate voltage, you are accumulating the electron in the channel. Now, when you apply the gate voltage 2 as negative, you are accumulating the holes. Okay, so these electron and these holes, by applying the 2 opposite gates, positive and negative underneath, they will form the negative charge and positive charge island very close to each other, and they form the PN junction, electron and hole. And they were very close. There will be a sharp junction you can see between these 2 gates region. Okay, and when you shine the light on this material, there will be a lot of, electron and hole pair. It can generate, MOSE2 material itself. Okay, and then you apply the source drain voltage, or when you don't apply, you just connect that, you will get the current. Okay, it will produce. So this gate 1 and gate 2 are important. Now you see that this is the current and voltage measurement with one of the diode, which is called NP diode. N stand for positive and P stand for negative. Okay, holes. You will see that this is the NP diode. The rectification is one direction, and in other way, if we will alternate the positive and negative gate voltage here, you will see the rectification of current is other way. Okay, so completely diode like behavior that you can get. And when you shine the light, this is the SEM image of the device. When you shine the light, some of you, if you working on the solar cell, you put measure the current by applying the voltage, and at 0 voltage you can measure the current here. Okay, with shining the light. And that current is called a short circuit current. When the current will be 0 at certain voltage, that voltage is called as open circuit voltage. So these 2 parameters are very important. You need high open circuit voltage, you need high short circuit current, right, to get the higher photovoltaic efficiency. And this is the power generated. So power is equal to just voltage and current. P is equal to V times I. Okay, and you can get the power, electrical power, it generated from this just few atomic layer of this photovoltaic solar cell. And we estimated that this material is probably around 10 atomic layer of MOSE2, okay, which is like kind of a, you see, transparent. You can see the electrode underneath, which is like a transparent and flexible. You can achieve the efficiency 14%, which is very close to the silicon silicon solar cell that we are using on our top of the roof, right? The silicon solar cell is like a 15% roughly, okay, 15 to 20% efficiency. And these are the thinnest possible materials, okay, transparent materials. You can get the high photovoltaic efficiency. Okay, so not only the electrical properties or the optical property where you can use photovoltaic solar cell or the photodiode. you can think about, because these are like a thinnest possible materials. These are sensitive to the light, okay, strong light matter interaction properties, and you can modulate the charge carrier. That's the important. You apply the gate voltage, positive gate voltage, you can put the electron inside this material, you apply the negative gate voltage, you can put the holes inside the materials, then you can actually configure these materials in many different type of application. So one of this one, you can see here, this is the optoelectronic switches we discover, okay? So you are not applying any gate voltage and just measuring IV curve, okay? Apply the voltage, measure the current, and no optical signal also in this case. And you can see that this is non-linear behavior of current. We can see in left hand side, in negative side, there is no current. Right hand side, there is a little current. We got like a rectification. So this looks like a diode, okay? Diode rectification that we saw before. Now, if you shine the light, let's say 30 microwatt, you can shine the light and you apply the positive gate voltage, this one, and the blue one, and you can see that the rectification increases in positive side, but there is no current in negative side. So the rectification of diode-like phenomena increase with positive gate voltage. Now, if you switch the gate voltage from positive 7.5 volt to negative 7.5 volt, you see this one, okay, orange color. The rectification changes the direction. It goes to the negative side, positive side. There is a little current, of course, but it is like very small current. So this one, let's look in logarithmic plot. This is the logarithmic plot of this graph. You can see this completely diode-like rectification in positive 7.5 gate voltage, and the rectification of current just alter, okay, changes the direction when we switch the gate voltage from positive to negative, and we fitted with diode-like fit, actually rectification fit. N is called the rectification factor, and here you can see that N is completely like a theoretical values, which is 1, okay, factor. And this one, you can see that any optical signal, let's look, okay, where you can use it, okay, apply this device. Any optical signal is coming, you want to send that signal either one side or another side, 2 different area, let's say, 2 different places. So you can have a switch, this kind of switch, and this switch will work positive and negative gate voltage, okay? You can turn the positive gate voltage, your signal will go to one direction. You switch the gate voltage to the opposite direction, the switch will direct the optical signal to the other direction, okay? So that's what we also patent this one, which you call the optoelectronic switch, okay? So there are many different types, okay, of electronics or optical devices that you can make using different configurations of these 2D materials, putting on the top of each other, called heterostructure or even a planar structure, okay? Probably I will conclude here. We discuss in this talk how these 2D materials can be used for efficient different polarity of field effect transistor, N-type, P-type, without doping, okay? It just comes like that, okay? And also ambipolar type of field effect transistor, where you can use for complementary logic in CMOS devices that we are using today. We also discuss about the photovoltaic efficiency, just few atomic layer of these materials, thinnest possible materials, have strong light matter interaction properties and high photovoltaic efficiency, okay? So they have the interesting optical switches and also photodiode, high responsivity photodiodes that you can make using these 2-dimensional materials. Okay, so with this, I would like to stop my talk here and thank you everyone for being here. If there is any question, I will be glad to discuss about that.
Yeah, good morning, good evening, Dr. Nihar. I have a quick question. I mean, you have given enormous information about 2D layer graphic electrical conductivity, and you have also given excellent research work on light matter interactions, photo detectors, and using application safety, security, IR detection. I have a quick question related to. Did you try other wavelength for tungsten diselenite light photo detectors? I mean, I can see that 532 nanometers you have used it. You have used,
Yeah.
and you
Yes,
got like 20,000% efficiency. And did you try various wavelengths? I have seen the spectrum, but I missed that. I think you have chosen the particular wavelength for that. Would you please explain that? I just
this
missed
one,
that point.
are you talking about the photo detector?
Yeah.
We tried actually several wavelengths. Okay, this is in different materials. So these materials, as you can see, the band gap of these materials falls in the visible region. Okay, these are like 1.3 electron volt to 2 electron volt band gap. So they absorb very strongly within that region. Now you go, and the photo detector works pretty well with high sensitivity throughout this, visible region. But when you go to the infrared, okay, 950 nanometer, then the responsivity decrease because the band gap does not allow to absorb. Okay, you reach the band edge of these materials, they will not absorb. The absorption of the infrared wavelength is very low, so responsivity is low in that case. But there are other materials, okay, you don't need to worry about this. Other 2D materials, for example, black phosphorus, we discussed, we recently did, I didn't show here that we developed the infrared photo detector, okay, using MOS2 in different technique, because sometimes even though there are some electron hole pairs generates at 950 nanometer, okay, wavelength in infrared wavelength or near infrared wavelength, if you are measuring, you can see the two terminal method. Then the small amount of electron hole pair, probably you are not able to catch it. Okay, they suffer with scattering, they suffer with the Schottky barrier height and so on. So we improve that, and there is the possibility that you can get, even these materials can be used near infrared high sensitivity photo detector. Now, in addition to that, particularly if you are looking the infrared photo detector, probably 1000 nanometer to like a 3000 nanometer per infrared, okay, you can use other material which has low band gap. One of them is the black phosphorus. Okay, black phosphorus has the band gap 0.2 electron volt. Okay, and it can absorb enough, okay, light, and it can produce like a high efficiency till far infrared.
Okay. Thank you. I have one more question. Sorry. The question is, in optoelectronic switches, how do you control the thickness of layers like MOAC2 and electrodes gold layer, BN layer? I mean, what method you have used to control all this stuff?
Okay, here in this case,
yes.
So far, okay. Now the people who were CVD grown, okay, groups, okay, they were trying to, they know how to grow the BN, boron nitride, which is the dielectric, high K dielectric, and that's nice, okay. And now they were trying to grow different 2D material semiconductor on the top of BN, okay. But so far, not a very good rate of success for growing the high quality. But for in this case, what we did is we manually transfer. We exfoliated by using the Scotch tape. Then we have a transfer station, exfoliate the single atomic layer or few atomic layer in one of the silicon wafer. Then we etch it and take that, okay, manually, and put it on the top of another.
Okay.
Yeah.
Okay. Right. Thank you so much. Yeah, you can ask other participants. You can ask questions related to the presentation, or maybe if you have any other question, also you can ask him.
Yes, please. Oh, is there any chat room? Maybe there is a chat.
Yeah, it's there. It is there.
Oh.
Yeah, you can also post the questions in chat. Participants, please you can also post the question in the chat box.
Okay, I don't see that. I mean, question. Let me see.
Kanchanlata madam, are you there?
Sir, Pradhan sir,
Yes.
sir, is there any scope with the combination of indium for improving these, increasing or enhancing the properties?
What kind of properties you are talking about?
For electronic devices,
Yeah.
combination with indium.
Oh, indium or indium selenide you are talking, or only indium?
Indium selenide, any mixer.
So indium selenide, as I didn't talk about that, but I saw you one of the thing that we are working on that. You can see that indium selenide something which is pretty interesting, and I didn't talk about that. Why this indium selenide encapsulated with actually polymer layer? Okay, on the top there is a polymer dielectric layer, just the encapsulated, and it increased the mobility so high, like more than like a 3000 centimeters square per volt second. Okay, when you do this without encapsulation, it is less, probably close to 800 900, of course. Okay, but not this much. But with encapsulation with a high K dielectric material, what happened is you can reduce many, like a polar, I mean phonon scattering or many other scattering mechanism. Okay, that's why it increased. So there is a lot of actually work going on called dielectric engineering. Okay, different dielectric, how we can combine them with these 2D materials, and that will enhance the electronic properties of this material. And you see, this is 3000. So it is already proven that these materials can be used or replaced with the silicon MOSFET already.
Okay. Oh, what dielectric material you have used, Niharji? I mean, what did you?
So far, there are a lot of like work I have done so far is on silicon dioxide, okay, dielectric. But we are using the boron nitride. Boron nitride is one of the great, dielectric material, because boron nitride is like a graphene structure, right?
Yes.
It is like a smooth, boron and nitrogen, they were just in one plane, okay, 2D plane. So this is like a most nicer dielectric material that you can use for the two-dimensional other electronic devices. That's why people are using this. One is black phosphorus. It is encapsulated with boron nitride. There is a top BN and bottom BN. Okay, that's why they actually enhance the mobility to so high, 4000 centimeters square per volt second at room temperature. Okay, but still there are a lot of work is going on in BN, because it is very difficult to fabricate the BN with like a large scale.
Yes.
BN can survive only hardly 1 hour in oxygen. Okay.
Okay. Yeah, thank you. I think I can see one question in chat box. Maunika, how to start simulation of PV array of reconfiguration technique using MATLAB's simulation?
Well, I think there are many people. There is a, semiconductor simulator available. Okay, I don't. I am not theorist actually. I don't do simulation, so I'm not sure. But there are many. For particularly 2D semiconductor simulation techniques, I saw people are using from. Many group. I saw few group. If we'll follow the Stanford University group, there is a huge theoretical group. They actually develop their own codes, own everything, software to simulate this. But there are, I think, software available to simulate. Yeah.
Okay. Any questions from participants? If I don't see any questions, so I would request Dr. Kanchanlata Madam to propose a vote of thanks for the Dr. Nihar Pradhan.
Yes, sir. Sir, it's my privilege to propose a vote of thanks speech on this day. Nihar Pradhan, sir. A very awesome lecture, sir. Yours is in a simple way you explained all the effects in this, and a warm and graceful day to our honorable resource person, Dr. Nihar Pradhan Garu. Thank you, sir, for giving us a blueprint about the theme of the program. And he is starting lecture with a famous statement, the plenty of room at the bottom. Because of him, how tremendous growth occurs in electronic applications from 1956 5 MB hard drive to 2020 1 terabyte flash drive. He explains the importance of layered materials which have special properties like flexibility, transparency, and if we synthesize that materials in large scales, we can fabricate devices from solar cells to spacecrafts. And in this, graphene material has play a vital role for fabricating these electronic devices, which are cost effective and eco-friendly way. And he is explaining this very much, very, very flexible, he explains, and some materials like molybdenum sulfur dioxide, sulfur disulfur material as PET, and if molybdenum is sandwiched between sulfur layers using chemical vapor deposition method and chemical vapor transport method, that reduce it to 2D atomic layers to 10 atomic layers, how their mobility increases also explained in an awesome manner, and how tungsten diselenium material as a phase shift modulator, indium selenium as PET, and black phosphorus PET, if it is increased to layered structure, how they can exhibit a special properties, and there are, and he explains about the challenges like electron phonon scattering, Coulomb Coulomb impurities, surface optical phonons, surface roughness, structural defects. If we decrease these effects also, we can gain a large production of electronic devices. And he explains Oxford butterfly effect, and how if we increase the layer structure of graphene, that bilayer graphene will become a superconductor. Means if we put a second layer in rotational motion with a increasing of angle from 1 to 1.27 degrees with a light increase of rotation, then that graphene material, two-layer graphene material will become a superconductor. And he explains about the theoretical Van Hoff singularities. Because of that, this molybdenum disulfur, tungsten diselenium, indium selenium act as high sensitive photodetectors, and how few layered tungsten selenium has quantum efficiency increases by 20,000%, and how these materials act as solar cells, photovoltaic cells, and optoelectronic switches. With this, we are very thankful you, sir.
Thank you
On
very
behalf
much.
of the entire fraternity of this program, we extend my heartfelt vote of thanks to our resource person, sir, who spared time from his busiest schedule to share your knowledge in the recent trends of optoelectronics in platform. Thank you, sir.
Thank you. Thank you very much.
Thank you
Thank
so
you, everyone.
much, Nihar Pradhan ji. Have a
Thank you.
good night. Thank you so much.
Thank you. Thank you.
Yeah. So, madam, are you there?
Sir, yes, sir.
Yeah, I think you can start the next section too.
Okay. Now And this session, it starts with Parvatalu sir speech. I take immense pleasure to introduce the second resource person and convener of this international webinar, who has impeccable achievements in the field of physics. Dr. Paratalu Kalkonda is working as assistant professor at Government Degree College, Hayat Nagar, Usmania University, Telangana. His current research focus on developing the organic thermoelectric materials for flexible electronic industrial applications. He completed his MS and PhD from Worcester Polytechnic Institute, Worcester, MA Fluids. He was working as postdoctoral fellow at Carnegie Mellon University, Pittsburgh, USA, and was working in the field of thermal mechanical properties of polymer nanocomposites. He published in more than 25 international peer-reviewed journals, including Royal Society of Chemistry Advances, Nanotechnology, and Journal Physical Chemistry, etc., which are highly cited journal in scientific community. He is also a reviewer for Journal Physical Chemistry, Journal of Material Chemistry and Physics. He is a member of Material Research Society and American Physical Society. Sir,
Yes. Yes,
the
madam.
session. Please start the session.
Yeah.
Thank you.
Yeah, thank you, madam. Thank you, Dr. Kanchanlata, madam. Yeah, thank you so much. So today, myself, let me introduce again myself as Dr. Parvatalu. Yeah, I've been working in as assistant professor, GJH 8th Nagar, Osmania University. Without wasting of my time, so I'll be talking today thermoelectric performance of conducting polymer nanocomposites. So during my PhD, I was working on various liquid crystal nanocomposites, polymer nanocomposites, and basically we were looking thermal physical properties. And during my postdoc period, I was completely focusing on polymer nanocomposites in different perspective view. Like we were looking anisotropic mechanical properties in carbon nanotube polymer composites, and we were also looking at thermoelectric performance with conducting polymer nanotubes with various conducting polymers we have tried. And then we have published our work in various journals. And coming to today I'm going to talk thermoelectric performance of single wall nanotube filled with carbon nanotube polymer composite with P dot PSS. Coming to the I'm going to actually talk motivation, then followed by background. Then I'm going to talk objective of my this project. Then I'm going to talk about fabrication process and then results. Finally, I'll conclude the summary of my work, and I'll also talk about the applications. So motivation for this project, basically until now we have been using the fossil fuel as being the common energy resource in day-to-day life. We have been using the fossil fuel as a common energy source. However, fossil fuel has the issues with pollution like air pollution, acid rain, water pollution, earth warming. Due to carbon dioxide, especially, it causes the environmental issues, which is the burning issue over the globe. So the main challenging is to convert the electricity from the waste heat. We have to be produce the green energy. So and the challenging is the we have to minimize the completely pollution and produce the energy, green energy, right? Coming to the thermoelectricity, the first who developed the thermoelectricity by Seebeck in 1822. And what he did, yeah, as you can see here, the simple setup, he applied the heat for a wire, right? And you can see there is a, two junctions, cold and hot junction. Then he observed the deflection here. You can see here, he observed the deflection in a magnet needle due to the electric current. The amount of induced EMF, which is actually responsible to generate this deflection, okay, which comes from the temperature gradient. Okay, we have the high temperature, the other side is cold temperature. But what happened actually when you apply the heat? What happened for the material? So when you apply the heat, definitely there is a diffusion, right? So as you know that the material has electrons, and then when you apply the heat, there are the phonons. So there would be interactions between the phonons and electrons. And when you have the high energy electron diffusion, you can see right side, when you have the high electron diffusion, you have a more current. When you have interaction with phonons, there is a transfer of their momentum to the electrons, which actually improve the thermoelectric power. So thermoelectric power is basically we are producing from the electricity from the waste heat. And you can see in the right side top, there is an equation which we call figure of merit or thermoelectric power efficiency. What is this? Zt is equals to S square sigma T by K, where S is delta V by delta T. And this is a very important equation, and we need to understand what are these factors S sigma K T. So I'm going to talk about this, how do we improve the thermoelectric efficiency with using the organic material. That's my challenging one. So which could be useful in flexible electronics. Okay. And now here thermal conductivity is the important one to discuss for this. As Dr. Pradhan was discussing about the scattering regarding the conductivity, which is also responsible here. So, thermal conductivity here, we are looking very low. We don't want thermal conductivity high because in order to increase the Zt, thermal power efficiency, we need to minimize the thermal conductivity. And we need to increase the electrical conductivity and thermal power at room temperature. But what are the best material? What are the ideal conditions in order to increase the efficiency? The first thing you can see here, low phonon flow. For that, what we have to keep the constant temperature difference, which makes the low thermal conductivity. And we are looking at high electrical conductivity, and the numerator is there, and that will come from the smaller resistance, a small resistance, and which makes you high electrical conductivity. So for that, you need to have the high energy electrons. And we are also looking the S should be high, S square sigma T by K. So S is also should be high. How do we get S? Seebeck constant. So we need to have the large voltage per unit temperature difference. As I discussed in the previous slide, delta V by delta T. So when you increase the voltage difference per unit voltage per unit temperature difference, we can make the sigma, S should be high. The next question should be, what are the suitable material? As you all know that metals, we know that metals, insulators, which metal I can use it? Especially you can clearly see that for metals, electrical thermal conductivity is high, whereas Seebeck is small. Coming to the insulator, Seebeck coefficient is high, thermal is, it doesn't have, and electrical conductivity is very low. And semiconductors are acceptable material, we can use them because they have the electrical thermal Seebeck coefficient. But the problem is that they are brittle material. So we cannot use them. They've been using for various applications, but if you are looking for the flexible electronic applications, and these material cannot be used. What are the material that can be used? I mean, as you know that nanotechnology allows the constant can be controlled independently and precisely. And I would definitely go for the, we would definitely go for the, I mean, polymers. I mean, how do we decide polymers? Definitely they are very flexible. And the question is, the polymers have the low conductivity, low electrical conductivity. How can we improve it? But there are conducting polymers are available, and we can use them and to improve the thermal power efficiency. I mean, you can also see here the thermal conductivity comes from two contributions. One is the lattice contribution, the other one is electrons contribution, right? And you can see here the polymers are the material which has a very low thermal conductivity, and that is very important for our work. So we need to keep thermal conductivity as much as low down, right? And what are the other materials that I can use it? So as you know that nanotechnology, carbon nanotubes, we have been using the single wall carbon nanotube. As you know that carbon nanomaterials, carbon nanotubes have the excellent thermal conductivity, excellent electrical conductivity. They have a mechanical strength is very high, and they're very stable, even very, very high temperature, right? And they are also they have a higher surface area and volume. And these are the properties of the nanotubes makes them good candidate to use in flexible electronics, right? And what are the polymer that we can use it? Sorry. And we can look the conducting polymer, as I mentioned. I mean, conducting polymers, we have the best polymer, which we call it P dot PSS. And P dot is an excellent oxidizing agent and charge compensator. And you can see the structure of the P dot PSS. Okay. And PSS is the top one, P dot is the bottom one. Okay. And the electrical conductivity for this material obtained as 1000 Siemens per centimeter after doping some polar solvent. And this is there in the literature. Our challenging is to using this polymer and carbon nanotube, we have to improve the thermoelectric efficiency. And in the literature, I mean, the scientists have been, improving the efficiency by various fabrication method, by various, materials. Here, there is a group from the Texas University College Station. They've been working in this field for, more than, 15 years. And they have been, trying to improve the jetty. And you can see they have improved the jetty to 0.4. And that too, they have used P dot PSS and DMSO doping. But we have started from here. So since they go to 0.4, our challenging is to improve that value. How do we improve it? So our fabrication method could help a lot to improve the thermoelectric efficiency. The question is, the main objective of this project is make a light, flexible, organic device with a high thermoelectric performance, like making a flexible TVs, flexible laptop, flexible phones. These are really wonderful applications. And the material that you've been using, single wall carbon nanotube aerogel. How do we make aerogel? Yes, we can make aerogel by CPD process. First, we have to make hydrogel. Then we need to go for the drying process, CPD drying process, in order to get high porous, very high porous. You can see here 99% of the porous material with the 3D structure. And we measure the thermal conductivity is 0.05. And the conductivity, the polymer which we are using is P dot PSS. The conductivity already mentioned is 1000 Siemens per centimeter, which is 1 lakh Siemens per meter. And you can see our samples on the right side, aerogels. What are aerogel? Aerogel is a very light material. Even if you blow it with your normal breathing also, you cannot stay. it just go away. And you can see quarter here, and then we place the cylindrical samples, and flexibility also you can see. We use this bottom one is we use that to conduct to measure the electrical conductivity. And the challenging is here is to improve the ZT more than 0.4 by using semiconductor device, brittle material. They have been achieved more than 3, but the brittle material, we cannot use them in flexible electronics, or we cannot use them like a tape. The purpose is we have to make a material like band-aid, like you can just place it device and it just absorb the heat and produce the electricity. So in the recent year, the development of organic thermoelectric material has received a special attention because of easy fabrication and also the cost effective, very less financially, very cost effective, very, very low. And the challenge is here is, important. There's a question about the organic thermoelectric material. Important, still an unanswered question. How do we improve thermopower efficiency of the conducting polymer nanocomposite by decoupling S thermopower, Seebeck coefficient, electrical conductivity, thermal conductivity. And here you can see the graph here, okay? When you're trying to increase the electronic concentration, the problem is here, Seebeck coefficient decreases, electrical conductivity increases. So, I mean, your goal is to increase the sigma, of course, but you don't want to lose S also. So there is a, challenging methods, fabrication method. We have to, tune all factors, porosity, volume fraction, everything we have to work out. It's not easy. Sometimes it takes years to control all these parameters. So, but if it works, I mean, it worked as at particular conditions. So you can see here fabrication method, material especially. These are the hydrogel. I mean, you can see clearly here hydrogel sample, rectangular sample. It's like a water, right? We just took it out from the petri dish, and when you do the critical point drying process, we get this in the left side one, like completely water out. It becomes aerogel. Only air is there. Completely 99% for us. And the structure you can see here. SEM, scanning electron structure, you can see completely 3D network, right? And there is a paper came from our group, Nature, in 2012, before I joined in this group. They have published this work in the Nature. And you can see they have tested the only aerogel sample, carbon nanotube aerogel. And they have measured the, stress versus strain curves. And they have checked this elasticity behavior, and it was really wonderful. It worked like a sponge, and that was a really awesome work that made me to join that group. And coming to the sample fabrication process, so first what we have to do, we need to take the P dot PSS is the solution, conducting polymer, and we need to add the DMSO, which is actually polar solvent, okay? And then we need to go for the sonication. So finally you get the concentration, 0 point, and then you have to parallelly have to make this single wall carbon nanotube gel with a concentration of 0.3, which means there is water is there inside, right? And then we need to mix these two gels, which is a coagulation process with a ratio of, we have done various ratios at this particular ratio of CNT versus P dot PSS, we got a really, improved this thermoelectric efficiency. And this is a, fabrication process. I mean, this is also schematic, how the anchoring of the P dot PSS on the nanotubes. So how it should increase the electronic transport. Because, as you all know that whenever you see the carbon nanotube junctions, you have the junction resistance, contact resistance, that we have to minimize. So with the help of this P dot PSS, will minimize the resistance and increase the electronic transport. And here you can see the structure, how it changes when you add the polymer. And from left to right side, when you add the P dot, what happened? The leftmost one is the single wall carbon aerogel. When you add the polymer at 2% volume, there is a small, you can see there is a coating on the nanotubes. When you increase the polymer concentration, P dot PSS, there are a lot of polymer coated on the nanotubes. I mean, you can also see the porosity also decreased. The interaction increased. Polymer with nanotube, the interactions are increased. Okay, that would also increase the electrical conductivity. But we have to be that decreases the thermal conductivity. We don't want that. We want to increase the electrical conductivity, but we have to control the thermal conductivity should be minimum. How do we control, sir? Definitely we can control it by the porosity, like keeping the volume fraction, controlling the volume fraction. So not to go for high volume fraction. You can see here the graphs here showing like electrical conductivity as the function of volume fraction, and how as you can increase the volume fraction at about 75 volume fraction, we got around 200 Siemens per centimeter, which is very good value. This we achieved only when after DMSO treatment. And you can also see right side DMSO post treatment. Initially we mix with the sample, then we also did the post treatment. And what is the importance of this post treatment of DMSO? DMSO, as you all know, that this is a solvent. It's a polar solvent. As I mentioned in the previous slides, P dot PSS, in which P dot is a conducting one, PSS is an insulating one. When you do this DMSO treatment, post treatment, means after making the sample, we soak into the DMSO. What does it do that? I mean, we believe that it just remove the part of the PSS content from the P dot PSS. So removal of the PSS content definitely increasing the P dot content, which means we are improving the electronic transport. So that also goes for the increase of the electrical conductivity significantly at some after 3 hours. But behind we also observe that electrical conductivity fell down. That could be maybe it's removing most of the PSS, and maybe the bonding between P dot and PSS completely collapse. Maybe it didn't work it. So that was our assumption. So basically, the electrical conductivity significantly improved about 75% volume fraction after 3 hours DMSO post treatment. Then here you can also see the electrical conductivity. Electrical conductivity as the function of the P dot PSS. So at this, we have, the composition you can see 1:2. So what is the composition? This is 1:2, like say carbon nanotube with P dot PSS. At about 1:8, we observe the electrical conductivity is very high. And you can also see here Seebeck coefficient. How does it change? I mean, you can see here it's almost like a constant. It's not changing much with respect to the P dot PSS. So finally, we also got the ZT as about 0.5 to 0.55. So we were able to improve the ZT from 0.4 to more than 0.5. So we are still working on the thermal conductivity measurement with the collaboration of the Michigan University. Because we got the thermal conductivity about 0.09, but this is fluctuating every time. So we were checking that value, and we have been collaborating this with the Professor Kevin Pipe Group, Michigan University. So you can also, I also shown here, schematic. You can see clearly here at the junctions, usually at carbon nanotube. These are the carbon nanotubes. At junctions, you have the high contact resistance. So we need to minimize that. So that to minimize that, we have P dot basically coated, anchored at that junction and reduce the resistivity and increase the electrical conductivity. The next is we also check the thermal stability with TGA, thermogravimetric analysis. Why we need to do this? Definitely thermal analysis is also important, because what is the stability? How stable this sample are? How stable this sample are, at what temperature? So we have done this analysis, and you can see in this graph, red one is the P dot basis with 1:8 sample, and even at 800 degrees centigrade, the samples did not degrade it. How? It's because of anchoring of the polymer around the nanotubes. The interactions improved, the structure improved it. If I keep single polymer, definitely it burn it. But if I keep the composite, it didn't burn it because of nano confinement. So thermal stability improved 60 degrees for composite sample. So we are also looking actually what are the causes, what are the factors that that are helping to improve the thermopower. So definitely heat flow, we did this experiment with DSC, differential scanning calorimetry. What does it do? We can see simply in the graph heat flow versus temperature. It's about 250. You can the peak shifted. See the pristine, the pure polymer. It is a broader peak, but when you coated with soaked with the DMSO, the peak becomes steeper, which means there is a structural changes. For the composite sample, scaffold sample also at 75% volume, complete the peak reduced, the peak also still steep. That means what? In the structure is changed, there is a stronger interactions between the polymer and nanotube. The crystallinity increase for composite. When the crystallinity increase, definitely there is the stronger interfacial interaction between the polymer and nanotubes. And the Raman also, here we were, we were trying to understand the improve the thermopower with the help of the Raman scattering. What are the other factors maybe cause? Raman effect, Raman scattering can also give the information about the interactions. And as you can see here, there are peaks here, RBM peaks, and G band, D band. G band is in plane vibrations. D band is out of plane, and these are the defects. Due to defects, you can have these RBM modes. And you can see on the right side, I shown here for composite sample, green one, there is a shift in the peak. That also causes the improved the structure. There could be stronger interaction that would actually, improve the thermopower. And then finally, the important factor for the flexible electronics, mechanical characteristics. Two mechanical, you have to use this material for the mechanical, for flexible electronics, flexible TVs, flexible, laptop, etc. For that, we tried here to see the stress versus strain graph. You can see here the composite sample stress increased a lot, ultimate tensile stress significantly improved a lot, and also its strain also increased. As strain increased means what? The stretchability increased. And the right side graph, modulus, E is the modulus versus volume fraction, and it improved a lot at about 75% volume fraction. The modulus you can see here, it improved, modulus a lot, and also the other factor also important, ultimate tensile stress. That is also important, whether this is a brittle or brittleness. It helps to know the brittleness. If it is more brittle, we can't use them for flexible electronics. So, I mean, we have to control all this stuff. We don't want more brittleness. We want to use, we want to keep the material like a porous, a lower volume fraction, and increase the electrical conductivity, increase the Seebeck coefficient, and decrease the thermal conductivity. Of course, we can decrease the thermal conductivity by keeping the pores in the composite material. If you make the brittle material, thermal conductivity play very important. It increases anonymously. It increases like anything. So we don't want that. So controlling the volume fraction play very important role in this material, in this fabrication process. So here tensile modulus and ultimate tensile stress improved for composite sample. So we use here sample 75% volume fraction. So let me summarize the important points. So thermoelectric performance improved after post treatment of DMSO, and we got electrical conductivity 220 Siemens per centimeter, thermo power 80 microvolts per Kelvin. Thermal stability also improved, mechanical properties also improved, and we finally, we may get more, but currently we have been getting the 0.5. There are plenty of applications. Once you can get this value, like, close to 1, we can use them many applications, like aircraft power generation from the solar. We can also use them charging devices. You can see this person, and you can tape it, and you can tape to your hands. It absorbs the heat from the sun and convert into electricity, and you can use that to your mobile charges, phone charges, and you can also use it flexible electronic application, especially this play very important role, coolers and batteries, lot of applications. So this is a really wonderful research field to explore. And then I've been working on the proposal to submit thermoelectric performance of organic thermoelectric material, and definitely I hope I'll be submitting very soon to DST. And one more project related to the electrically conducting, mechanically robust, ultra surface area carbon nanotube aerogel composites. This is we are looking like guards, like security, like protective layers for helmets applications, and very brittle material, like robustic applications, like sofa sets. We can use this kind of material, mattresses, lot of applications out there. So, and I would like to thanks to all our collaborators. I've been working, my PhD advisor, German Aquino, Muhammad Islam, my postdoc advisor, Sam Sekab is my also LBL National Laboratory USA. Is my postdoc advisor, another postdoc. Kevin Pife is our collaborator. John Mellon is also our collaborator. Charles Rosenblatt is from Case Western Design University, and Professor Rajrathan Basu, US Naval Academy. Professor Ali Kambusani is from Harvard and MIT. He's a wonderful professor to work, nice person. There's another professor from Arnab Payne, is from Coast, KSC. I also spent a few months at IISc Bangalore. I was working on optics related stuff with Jaydeep Basu, Professor Jaydeep Basu in physics department. Publications in various journals you can see here, and then coming to the questions. Thank you so much. Thank you for your attention. Please, it's open for the questions. Thank you. Kanchalata madam, can Can you take over? Dr. Kanchalata, madam?
Sir,
Yeah.
sir, how thermal conductivity is measured, sir? Which method?
Madam?
On which method you follow thermal conductivity?
Thermal conductivity, actually, there is a, we have developed, we got it from the DSC, also we extracted, but that is actually, fluctuating every time. It's not exact method. I also developed the small design, madam, in my lab
Okay.
with a thermocouple, all the simple setup. During my PhD, one of my, minor project for undergraduate to develop the thermal conductivity setup. So I was the, guide for him to develop that is major project to submit undergraduate. So it took 2 years to develop that setup. I used that setup also to compare the DSC method, kind of very close, and still there is a developed setup at Michigan University. They've been, I think they have developed long back, 10 years back, and been publishing papers with the, I think that is really good techniques to compare our results. So we sent our all samples to there. uh, most of the measurements are like, fluctuation, like, 5 to 10% results. So I mean, if you can able to accurate those results, definitely that is a really very good paper to go for the like advanced material, or maybe I don't know if it goes for the nature, I'm not sure. Yeah, thank you, madam.
Thank you, sir. Tea break, sir.
Yeah, it's a tea break. If anyone asks question, please welcome our participants. Otherwise, we have at least 10 minutes break. Any question from any students, faculty members? Yeah, otherwise I can conclude. Thank you so much for all of you. I would request all the participants should be here just for 5 minutes break. The other speaker will be here within 5 minutes. Dr. Datta, are you there? Datta? Datta? Dr. Datta, are you there? Right. Yeah, there will be a link for the certificate. We'll post it around 12 o'clock. So you'll be receiving e-certificate, participation certificate. So yeah, by this I think Debalina Datta is going to join in a few minutes. I think she joined. Dr. Datta, great welcome. Datta. Okay. Debalina. Okay, let me okay, I'll Debalina Datta. Okay. Where to Debalina? Yeah, you can. Oh, yeah. Yeah, great. Yeah. Yeah. Let me. Okay, madam. Okay. Give me 1 second. So I'll be.
Can you hear me, Prof?
Yeah. Let me. So good morning to all. Again, so there will be another speaker is ready now. There is another speaker ready now. I'm going to introduce Dr. Debalina Datta now. Again, good morning to all. So as you know that myself, Dr. Parvatalu Kalakunda, Assistant Professor in Physics, GDC HYT, Usmania University. It's my immense pleasure to introduce Dr. Debalina Datta for this one-day international webinar. Dr. Datta holds a PhD in Organizational Communication from Purdue University, USA. She is currently a senior lecturer in the School of Communication, Journalism, Marketing at Massey University, New Zealand. Her research interests are culture, diversity, inclusion, including how women in STEM, science, technology, engineering, mathematics, and medicine, craft their science of resilience and leadership in organization in the context of culture. Her work has been published in journals such as Journal of Engineering Education, Management Communication, Quarterly, among others. Dr. Datta has contributed to policy discussion on diversity, inclusion, and has conducted workshops with women and children on career. She gave the workshops in various countries too. So I believe that the faculty members and the students will be benefited immensely from her presentation and hope that you will enrich your knowledge can be useful in academics. Without wasting of time, now with this short introduction, I hand over to Dr. Datta. Over to Dr. Datta.
Thank you so much, Prof. Parvatalu, for that kind introduction. A very warm welcome to all the students, faculty members. Thank you for having me here. It's delight. It's an honor to be here. I'm super excited because definitely by now, you know, I'm not going to give you a lecture on physics. Now, that's not my domain, and that would be scary. It's really scary if I start teaching you something. So definitely not that. So what I'm here for, and for that, I really have to be grateful to Prof. Parvatalu, because I think he wanted you to have kind of a tasting platter of what it means to be a scientist and what agile careers and research mean. This definitely can be, this workshop can be under the aegis of what we call soft skill workshop, but not really that, because we are researchers, we do research, and whatever I'm going to talk to you or share to you today evening and your morning is all about research. And it's imbibed in research, and I hope you find this session helpful. As we have had the chance to discuss this format earlier, what I'd love to have is you in the chat box, so please feel free to interact with me. I'd hate this if this is a monologue. In fact, I put it in my talk schedule that this is going to be a dialogue, a discussion, like us coming together and discussing the topics that I would be doing today. So please feel free to jump into the chat box. Please introduce yourself. Please keep telling me how you like it. What else? If you have any questions, if there are any comments or anything that you've observed or the research that I'm going to share, this kind of resonates with you. So please go ahead and share. I'd be very happy. And we'll definitely take the discussion along with this talk. So welcome once again. And I would like to first begin with a short introduction of who I am and who I am coming in and giving you all this lecture that I'm supposed to give you today. So hello, everybody. My name is Devalina Datta, and I'm actually a senior lecturer in the School of Communication, Journalism, Marketing, Master Business School. Now, this is something that you would actually know by Googling me on the internet, but let me show you something that you might not find in the internet, but I hope that's equally interesting to you. So for me, I'll just go ahead and quickly span my research journey, the whole career graph, and put in front of you that what are the experiences that I have had that has such an impact on my scholarship. And will continue to have an impact on my scholarship as I kind of go ahead. So I would like to first begin with this wonderful quote that I found in one of the schools in Singapore. Not that I follow it, but I just loved it. So I'm hoping that you'd share some of my enthusiasm on that. And then moving on, I would like to start with my school and my higher secondary scores. I know they're very interesting, and why I put it out there is that in order to be successful in life, you do not have to be a topper or a high scorer or always score in those highest brackets, be the genius that you are. I think it's important to start humble and know where your strengths lie, and then probably move on from there. And that is why I would like to put in my mark sheet. These are my 10 mark sheets and 12. And you can see, like, I am the daughter of an engineer and a bank manager. Obviously, my parents weren't that ecstatic. Of course, it was a first class. Who cares if it was a second class as well? I think I wear this as a badge right now. And as usual, I tried for medical entrance or engineering, like all of us do, and we should, like, it's something like we have to do. And obviously I didn't get it right. So I was like, maybe it's not for me. And you can very well imagine that that is not something that your parents do want, right? They want you to be very successful. So my choice was then to get into botany, and I love the subject. And then I topped the university and the college. Here's a secret. I just didn't study to top. I just studied because I was scared I'm going to fail the examination. And that's why I studied very hard. But it was a very nice surprise. And my family just refused to believe that, I could get such a position, because they clearly knew what my mind frame was at the time. Moving on, I think then I moved to, and then I did have some job experience, and then moved to US. And I did my PhD in Purdue University in organizational communication. So Purdue University, as you know, it's a cradle of astronauts, and it has, I think, 11 astronauts, and I think the 12th one is also from Purdue. Last one is also from Purdue. It all started with Sir Neil Armstrong, and then it's kind of, the tradition is continuing. If you guys are ever interested in applying to Purdue University for your higher studies, go ahead and do it. It's an amazing institute. You should totally try it out. From there, I did my PhD and I was a BILSLAN scholar. Also, I did a short course in business, like it was applied management principles that I found was really useful. So this was definitely a scene where I see myself changing my career. So from botany, biology, in which I did my master's, I totally moved into a very unrelated yet quite familiar, very commonsensical, familiar kind of an environment that is organizational sciences. As you can see, at that time, I had a child, so I did it with a kid, and I did it in 3 years. So I was in a hurry to finish. My work, basically, my research that I do, it looks at the ways in which people who are at the margin. So, for instance, people whose career trajectory might not be traditional, how they go about crafting new careers, how they go about thinking about leadership, resilience, something that we will talk about later in this lecture. And the most important thing is, how do women in sciences, technology, engineering, and mathematics actually talk about sustaining themselves in careers? Most about how to marginalize people who are at the margins, the borderlands of careers, people who do not have any advantage in terms of their expertise. How do they make sense of who they are and then kind of craft their leadership journey into career? So that has been one of my interesting stuff, that stuff that I'm interested in. And what makes it so exciting is I did have an offer to present my work at a lot of national and international forums. I'm particularly proud of my association with United Nations Women, in which I regularly present my work. We talk about policy changes and effect that would have on the ways in which we can actually have more women and people from marginalized communities into the program. I was, interestingly, one of the top 10 Scholar Watch, in the top 10 Scholar Watch list at the Arizona State University Colloquium in Organizational Communication, something that it was really a pleasant surprise for me. Then moving on, the ways in which I do is, whatever I do, I give back, try and give back to the community. So you'd see a lot of my research ties back to the communities, and it talks back whatever I have found, my results, I try and make sense with that to people and tie it back to what it means to have this research. So for instance, if I talk about, women's education in science, engineering, mathematics, STEM, what does it mean for others? What does it mean for the grassroots? So these are some of the work that I do. You'd find me happily in some remote village, or with kids, or with young women, or with people, students, other students, both male and female, talking about my research and how it impacts them. My work has been covered, interestingly, in a lot of science outlets. So Asian scientists covered my research. Physics.org covered my recent research, was last year. If you're interested, I definitely would invite you to take like a screenshot of this and probably look it up if you're interested. And let me know if there are any questions or concerns that you might have. So this, in a nutshell, is who I am and what I do. So basically for today, what I would want to discuss with you is probably a corollary of my work, and it's about a dialogue on leadership, about resilience, and pathways to career and research agility. Now, when I talk about this topic, the first thing that comes to my mind is, guys, how do I convince you that this could be of interest, right? You would want to know that, okay, you're doing this and you have had amazing lectures since early morning. You have, heard experts in the field, and that's your field knowledge, your domain knowledge. How does what you are learning today in my session actually help you, or it makes sense? I'd probably leave you to judge that, but definitely I would want you to take a look at what I'm trying to convince you of today. So I'm going to go ahead and quickly talk about the domain knowledge. So as far as I know, like, you guys are into your graduate, postgraduate, and master's, PhD program, and henceforth. And one thing that we do is, what makes you scientists that you are, right? It's about your deep understanding of your field. Or in other words, in order to be a physicist or a chemist or a biologist, the first and the foremost thing that you need is the domain knowledge. So the domain knowledge, in other words, it's an understanding, it's a comprehension of the information about a particular topic in which you're pursuing your career. So for instance, physics, right? So you would have all the domain knowledge, all the information that you'd get It's primarily about the content of your work, right? It's a content of physics, something or the other. So Prof. Parvatalu, he teaches nanotechnology. So obviously you'd get a lot of information from him. And that would make you a specialist in that particular field. And we can talk about any field that we want to discuss here under the sun here. So it makes you, in other words, in very layman terms, specialists or experts in a particular field. And this definitely is dependent upon a lot of input from the teacher, from the books, websites, from your syllabus, your assessments, right? The discussion that you have around that topic. So whatever is your domain knowledge, discussion with your peers, so that is how your domain knowledge increases. Discussion with experts, right? So, for instance, Prof. Naveen, now his talk would contribute to your domain knowledge. And this expert knowledge that we talk about, or expertise that develops, which is primarily domain specific. So if I were to tell you that, hey, you are an expert in physics, or you're an expert in chemistry, or you're an expert in that topic. Well, we don't say physics or chemistry, we just go for, say, you're an expert in organic chemistry, or you're an expert in the fission of ions, then fission of atoms, I'm sorry. So then what happens is that expert knowledge is primarily on the domain. Does it make sense, guys? Like, can I have some show of chat? Come on. Can I have someone to chat with me? If this all makes sense, I'm just trying to get the chat box open.
Yeah,
Not very sure if it's opening. Lovely. Yeah, cool. So then what we do is we move on. We talk a bit about research. Now, whatever you know about domains, your knowledge, your textual knowledge, your content knowledge, the domain knowledge and expertise translates into you doing some research. So this was a very interesting cartoon from PhD Comics. I'm not sure if you read PhD Comics. So it was from an astrophysicist, Jorge Cham. And I think he made during his, I think he was in Stanford or Howard. And when he was doing his PhD, he used to do this, sketch this art. It's very entertaining to look at. I've put in the link in there. So if you guys are interested to look him up, he's very funny. So anyways, the point is when you are taking the domain expertise and putting that into research, the idea is that the research should be like, as I'm showing this figure on my left, it's supposed to be very nice and laid out, and you have all the ideas where this is going to. But in reality, your research is a very messy business. Now, how messy is that business and what needs to happen there? So in other words, research is all about, creative activity in order to increase the stock of knowledge, including man, culture, society, and all of that discussion also means that scientific research is a part of this. And if you look at the definition given by OECD, it's an economic indicator organization, it basically talks about research being a creative enterprise. Now, how many of us actually view research in that manner, right? Is it really creative? What's going on? And the most important question that I want to ask is, in what ways is this research relevant to you in your lives, okay? In what ways do you think you can be a good researcher? Is domain knowledge all you need? Is expertise all you need to be the best in your field or do your best in your career? So we probably will begin with that question, ask ourselves, as I go ahead and present 2 case studies to you, okay? Now, the first case study is about Rosalind Franklin. Now, a lot of you know that back in the 1950s, Watson and Crick won the Nobel Prize for the DNA double helical model. And they provided a model that looked at how the DNA of organisms is constructed. And the interesting part is, Franklin, it wouldn't have been possible without her. The one thing that happened was Watson and Crick and Rosalind Franklin, they started researching the DNA at the same time. Now, Franklin was working with X-ray crystallography, and Watson and Crick were just doing the 3D model at that time. Franklin had one of her lab mates, Wilkes, who didn't like Rosalind Franklin because it is said that she was a very uncommunicative person, that she was a troublemaker and she didn't get along with her peers. So she had a very problematic history with the administration. And so what happened was Franklin's picture of the DNA structure. This picture is a very famous picture up on my slide. It's called Photo 21, Photo 51, I'm sorry. Photo 51 was taken by Wilkes out of Franklin's laboratory and given to Watson without Rosalind Franklin knowing. So in a way, I don't want to put that term, but it's like stealing, right? So Rosalind Franklin's whole work was stolen from her, apparently because she was not very collegial to work with. So in here we are looking at, and then of course, when the Nobel Prize happened, nobody even acknowledged her because 4 years ago, she had passed away, and you actually can't give Nobel Prize to a posthumous person, so she didn't get the Nobel. And you've seen a lot of textbooks, and she was, of course, a biophysicist. Her work is completely erased, right? This is the first case. The other case is that of Konstantin Tsiolkovsky, and who is a Russian physicist, works with rocket. So he was into how rocket propulsion. And he's considered to be the father of astronomy and rocket science in Soviet Russia, because at the time when Soviet Russia was having this competition with US about putting people onto space, his work was a pioneer, right? Pioneer, groundbreaking work. And how fascinating is that? That you actually have that work, and that actually leads to a whole new vista of knowledge, like space exploration. But one thing about him was he was very reclusive. So all that amount of work that he has done, of course, this was useful, and it helped people. But would you find him as easily you'd find maybe some other astrophysicist or some other rocket scientist we know? Probably not. And this is also given in some research and biographies about him, that he used to lock himself up and not meet with people. So in both of these cases, there's something very common, and we're looking at it from a very historical perspective. The domain knowledge itself might not be enough for these scientists to get the recognition that they deserve. And isn't this fascinating? Like, can you tell me that on a 1 to 100, how much would you like to grade these two scientists on, like domain knowledge? Do you think they're experts? Come on, guys. You have the chat box. Talk to me. Do you think they're experts? Do you think they have the domain knowledge? Yeah? So I'm going to wait for your answer in the chat box as I go along. So if you have given me this answer.
Please use your chat box. You can ask you can give your response.
You can communicate with me. Please do. I'll be delighted. And I'm not sure why this is not opening. I'm sure it's going to open up. But the fact is that so when you give me the answer, and I probably will guess what this is. But hey, doesn't that put the earlier convention of domain and expertise of your discipline, of your subject, as the only thing that leads to expertise and recognition and success in research? We probably need to reconsider that notion that only domain knowledge is enough. So definitely there needs to be something else. So shall we explore what this is? So let me take you to some of the examples that I have curated from the web. And this is definitely a very recent one. So whatever research articles or research I'm sharing with you, they're very recent, and they would kind of give you an idea of what the field is like. So I would like to start with the first example. It is about astrophysicist Nargis Mehelwala, and what makes it so exciting is she's the first female dean of MIT School of Science. So isn't that fascinating? So somebody from the minority community actually coming in and getting that position is amazing. And what makes her interesting is not that, if you look at what the provost had to say about her, it has got nothing to do with her as an expert scientist. It's all about being a collaborative problem solver, a wise and generous colleague, a mentor, a champion of inclusive excellence. So definitely these are the terms that you definitely won't find in physics domain knowledge or chemistry or biology or any other domain of knowledge. So this is definitely interesting, right? So I have given you the link, so please feel free to look up the whole interview. The other interview is about a student who is from Quantum Physics Lab, Singapore. Again, Department of Quantum Physics in Singapore is very well known. If you're ever thinking of applying, please do so. And again, in this interview, we talk about how the programmer is talking about thinking, doing researching, extra challenges, having a good team. So it's nothing about, oh, I know amazing things, I have all the expertise that I need to do something. So a domain knowledge in that way is never complete, right? So now that you agree with me that there's something else that you need beyond domain knowledge, not the expertise isn't expertise, not everything there. So what is it that we need? And in here, I would like to introduce two terms for you. One's leadership and the other is resilience. Of course, I would like to begin with resilience first, but these are the skill sets that we need to equip ourselves as researchers, scientists in the 21st century. If you're really interested in how this works out or what's the base point, again, note that in this short lecture, all I can give you is a tasting platter. I can just give you some sample of it. And if you really like it, please feel free to contact me and I can direct you to some examples or literature that would further your horizons on this if you're interested. But this stands to reason that till now, whatever I have discussed with you, one thing is definitely sure, that you cannot go ahead and succeed just with having domain knowledge. There's something else that you need to put that impetus behind the role of a scientist or researcher that you're ascribing to your success. So what are these? So I would like to begin with resilience. So first off, a very simple definition that Koto gives of definition in the Harvard Business Review is defined like, okay, it's meaning making and capacity building. So capacity building is a very interesting concept that we talk about. Capacity building of human resources. I think that is the key or the DNA of resilience. In simple words, if we were to understand this, it's about holding on and making progress when we are down. It's about getting up and running after we have fallen down. It's about our resurgence. It's about the ways in which we reconstruct ourselves. We challenge ourselves in the face of adversity. We don't give up, okay? So that is a very crux, or it's the crux of what resilience stands for. There has been a very recent interest in how resilience might be relevant to the scientists or how resilience is important in your life. So it is important first to understand that resilience is not a personality trait. So it is not that only X will have it or Y has it and J has it. And that is why they are so resilient. You're not born with resilience. So that is one thing that the research establishes right away, that you are not born with this quality. This is actually inculcated. And that is a very important thing to understand, probably wrap your heads around. Levine in 2011, and Levine talks about this in the web magazine Science. She talks about how the career, any career in science, and I would say why science? I think any career these days, it's very demanding. There are a lot of hurdles and challenges when we think about doing a career right. Look, there are plausibilities here. You can totally do something not interestingly or don't put your 100%, but anything that you're putting in your 100%, especially in sciences and engineering, it's always backbreaking, it's always scary, and it's always ridden with obstacles. So a common consensus among the researchers or anybody who has done it, I think it's very commonsensical, is in academics or in any research, there will always be some setbacks or challenges, whether we like it or we don't like it, right? Most often we don't like it, but not that we have a choice, right? So each of us will always respond to the setbacks differently. And how we respond is never about whether we are born with that quality or not. It depends upon our backgrounds, our experiences, and our overall well-being. And I think traditional research on how scientists succeed, they've never looked at the concept of well-being. It's important to understand that resilience is very much linked to well-being, which means your happiness and your health, your mental and your physical health matters. It matters for your success as a scientist or a researcher. And this is a very important point to follow. A recent article in Nature, and if you look at the Nature website, you'd see this article was published yesterday. It talks about the strong links that one has between being a scientist, doing what you do in sciences, and taking care of yourself, which also means sometimes to walk away from what we are doing. This is very antithetical to what we are taught. We are always taught to, stop not till the goal is reached. Keep on working, keep on slogging. But as you are doing that, it's a great thing in, Proverbs, but as you're doing it, your body burns out, your mind burns out, and you do not have that capacity to go further. It is not a personal failure. It's just the ways in which our bodies are constructed. We're not meant to take up so much of strain. And it's a good thing to go back and think about our well-beings a bit. When we come back, it's a recalibration of ourselves that makes us way more competitive and better in what we do. So what are the strategies that you can think about in being resilient? I published a paper in 2019 in Applied Communication where we looked at the strategies that people from the margins actually do to become more resilient. And I think if we practice this and analyze, it's interesting that to know that you might not be tempted to give up so easily. So what does resilience do? Does it mean that we are amazing and we just come back like a superwoman or a superman? I think no. What it does is it gives us a new perspective of doing our work well. You might find that you'll have different ways of approaching a particular problem. So what are the strategies of being resilient? The first and the foremost thing is understand that there is a problem. So for instance, a lot of times we tend to ignore our health, and that might lead to a lot of problems. Or we tend to ignore, say, shortage of funds, and we go on. Or we tend to ignore that we are fearful in our minds to pursue something. So that real challenge needs to be actually identified by us in order to even begin thinking about resilience, something that we might want to do that. Next is understand our deeply rooted cultural prejudices. This is very interesting. Like, say, for instance, if you're a scientist, and I say this in a lot of literature, you'd find that scientists, okay, we are also governed by the patriarchal systems. Now, patriarchal systems is a system where, male child is favored over the female. That's how the societal structures work. It's very interesting to note that patriarchy also unfavors males in a very, how do I say this, in very fatal ways. So a lot of times we are taught that do not let your emotions show. So as a boy, why are you crying like a girl? So this whole point of crying or showing your emotion is considered bad. Research has shown that when you bottle up your emotion, it leads to a lot of stress in your life. So high blood pressure, diabetes. So when you see your dad suffering from that, you see that they are as much, victims of patriarchy as women are. And therefore, to understand some of the deeply cultural prejudices, it's very important to do so. Then the willingness to negotiate our identities. So for instance, you might start off thinking that you might achieve A, and circumstances change and you have to do B. So not giving up and recrafting yourself so that you're able to do B and doing it with excellence. Then identifying the resources to sustain your careers. Often we find that these resources are places that we wouldn't consider otherwise. The career support resources, the ways our professors, our peers can support us. Family is a great place to get support when we are stuck. So it's a great place for us to build ourselves, go for our well-being. Community resources, communities, well, sometimes, yes, no, I understand. I'm from India and I get that. What are you doing with your life kind of a discussion, right? Everyone's interested in a career. But if you have strong community resources, support, stronger family connections, they actually provide you with a lot of resource that you need to succeed. And sometimes you take that as well. So for instance, a word of mouth recommendation, somebody recommends you something, somebody provides you with some resource to apply elsewhere. So you get those resources, right? And then you craft your, you bounce back from your challenge in that way. Anticipatory concerns and career progression. This is a very fascinating topic. And this is something when I suggested, people were like, what are you talking about? So I argue that a lot of times when you understand and anticipate what's going to be there, and how it's challenging for you, you have more time to figure out ways in which how you're going to overcome that. So for instance, you might know in your career that you have to compete with a lot of other people. This is an anticipatory concern. It might not happen to you right away, but you might be thinking about a scholarship or an application for which you have to compete with a lot of people who are out there. So this is a plan that you have in mind. And then in your mind, you'll come up with a strategy or a number of strategies to overcome that. And that is the importance of anticipatory concern. So having that, right? anticipatory health and well-being concerns. So this is very important. How you're going to take care of your mental well-being and your physical well-being. Again, this has been a part of the conversation. It wasn't there before, but COVID-19 has forced us to think in so many different ways. So being researchers, being scientists, and being, normal human beings, we're definitely exposed to this new situation in our lives, in our countries, and in the world. So what are the ways in which we're going to overcome that? And in doing so, what are the new strategies of sustenance, of resilience we're going to adopt? Does it mean that you've given up on your studies? Definitely not. You probably haven't thought of how your original plans are going to work out, but you probably have something in place, or you may not be thinking about that. But definitely that you're here, you're struggling, you're doing so well for yourselves, talks about the fact that you are your own agents of resilience, and this is not something that we are born with. So definitely being resilient as a scientist or researcher is very important. And that is not a part of our domain knowledge. In fact, that is something that probably you're hearing from me from the first time, or you've heard of it before, you're just getting some reinforcement from my end. So this is about the whole crux of resilience. Next, I would want to look at the context of leadership and how leadership is relevant in our days. So it's very interesting when you look at research out there, it always says that when you're employed in an organization, the employer always looks for opportunities or places where you can show your leadership skills. So do you have interpersonal skills? Are you good with your time? Do you get along with people? Now, these are the skills that are not traditionally taught in any science curriculum. And you can talk about any curriculum in the world, not necessarily that's what you're following. So we usually don't do that. But beyond domain expertise is probably, there was a survey, it was like the 7th most important thing. First thing that people look for is, whether you are someone who can get along in the organization or not. So getting along with other people, it is considered to be a big skill, irrespective of what kind of job you do. And probably if I take you back to the example that I've shown you earlier in my slide, it does make sense, right? Therefore, it kind of comes together when World Economic Forum states that, by 2020, it's all about problem solving, creative thinking, emotional intelligence, interpersonal skills, both with normal as social beings, also around artificial intelligence. And these skills are not something that we can get just out there. You need to have some kind of leadership education or understand that you can be leaders. For most of us, leadership happens quite late in our stages. That's how we traditionally understand. It's like, we get into a career, we spend a few years on it, we gain the relevant, again, domain knowledge or expertise in it. And then we slowly think about, doing leadership, get into leadership position. But even if you get into that, nothing prepares you for what is there, right? It just doesn't take into consideration about all the important things that you need to know in order to be a good leader. And that is why I think bad leadership is a very endemic thing. Think about all the times you were frustrated with somebody who wasn't good at their job as leaders, right? It must have made you really upset. And the part of that is because of the lack of training that we have as leaders in the sciences. And as we get into an organization, every organization tends to see us as a future leader, as a potential leader. So definitely there will be some consideration that would be given to you in the decision whether you're going to be hired or not. And I'm talking this about Jensen's research in 2015. By now, well, that's a norm. So what does it mean? So Bass, DeWest, and Peyer into 2020, it's a recent article they have published in Science, and they talk about how PhD students like you, me, when I was at this stage, we are not trained to be good leaders. We are always trained to be domain experts. Now, if we are not that, if it's haphazard and absent, what are the ways in which we are not serving the society? What are the ways in which we are doing ourselves a disservice? The research is that in order to be good scientists, leadership is very essential, or researchers for that matter. In order to have agile careers, you need to look at your own ways of how you practice leadership. Part of that is you must be able to relate to others, understand, and manage and understand yourself. Now, these are the stuff that you do not pick up in any domain knowledge class. These are the stuff that you need to be prepared for. You need to be readied, if you will. So those are what gives you the agility to do well in your career in addition to your domain knowledge. Why do you need it for? So think about the ways in which you are competing for grants, or think about the ways in which you work with the team. Think about the ways in which you are going to explain your research to external stakeholders. And on the basis of that explanation, you might want to get some resources from them. Think about the ways in which you understand your strengths and weaknesses and how you want to make that as a part of your research journey. And then we come and think about how leadership then is not a personality trait. And this is something that we need to understand, that earlier research in leadership always talked about great leaders. So we're talking about the First World War, Second World War, 1920s research onwards. So it was about, about Stalin or Hitler in a bad way, about how leaders are born, they are not made. Now that research is inherently very problematic, and it favors one kind of leaders over another. So therefore, the debate whether leaders are born or leaders are trained, I think it is more tilted towards that leaders are trained. So it's important to understand that we are not born with leadership skills. Some of us even can't talk. We're shy, we just don't feel like expressing ourselves the way somebody else would. What do? Are we not leaders? Don't we have other skills that makes us leaders? So definitely these are some of the questions that we need to ask ourselves. And it's definitely valuable for scientists that Hurst talks about, is to think how doing science is essentially doing business. You are dealing with people, and you need to understand that how working with grant, convincing or persuading people about your research, setting up your team, getting your research out there, having people on board, getting your patents into marketable commodities, they're a big part of science, right? So think about this thing, and I give you the example of Apple, and we had that example early in the morning in the discussion. So you know that how whatever technology or science, whatever byproducts we have, whatever innovative products we have, it all comes down to whether the market accepts or not, whether it goes down to people or not. And a scientist is very much involved in all the steps to convince people of their product. So in some ways, Hurst says that he draws parallel between what scientists do, and he talks about how these concepts are valuable to learn. So the understanding of Hurst is then that you really need to learn about leadership. You really need to understand the tenets of what makes a good leader in order to understand how this works, or how your research or your career as a scientist can take off. Moving on, then how does one acquire leadership skills? Now, this is a very interesting topic from the American Management Association, and they do talk about this a bit. And I'm just going to give you a small tasting platter, as I've said earlier, because we do not have the time to spend a lot of time. But if you're interested, let me know and we can discuss this. So first, you have to understand that leadership is not a stable entity at all. So we do not sit in a chair and we don't practice leadership, because the world is disruptive. The kind of careers that you have is disruptive. Science changes every minute with new discussion. You have new paradigms of knowledge. And so it's important to understand that the leadership, enactment of leadership, or how we do leadership also changes versus the stability and the disruptive kind. So if we are staying in a virtually disruptive and a volatile world, it stands to reason that the leadership that we practice cannot be stable. So really understand that leadership is a very uncertain business. We will also stand up to the new challenges and opportunities that come every day. And this could be man-made, or this could be through artificial intelligence, and this could be through the immense development that happens through technological innovation. So every moment our world is changing, and it's important to be open to those challenges and opportunities, and to understand that whatever we are studying, that could be irrelevant in even a second, right? Something new might come on. And I give you the example of structure of an atom, or light as a wave or a photon. So what is it exactly? Or that light can change according to how the observer observes it. Now, all these come together, and you're looking at different kinds of knowledge. The structure of an electron, how it changes over time. And I don't have to give you an example of that, but to know that you need to be open to these new things that are coming up, and the ways in which it affects your marketability as a researcher or a scientist as well. Putting people first. Now, this is something that we are not inherently trained, but that is what we do, right? So when we're trying to solve, as scientists, we solve problems. As researchers, we solve world's problems. what is the point of a problem that does not put the interest of the people first? If we do not put the interest of the people first, then whatever we come up with will not go into a mass appreciation situation. So it will not be taken up by the people. By putting people first in the things that we do, we not only practice leadership, and these people could be the people from whom you are doing your research. This could be people who are working for you. This could be the people with whom you're collaborating. So this definitely takes a lot of those community-based values, if you will. And I think we do that well to work with people, whether we're doing that or not. Address issues that concern us. So it makes sense completely to talk about COVID-19 at this point and look about build upon the work that has been done before and not do something that is not relevant to our lives anymore. Having high moral and ethical standards is very important. So as we are looking at all this, all these injustices and frauds around us, I think it's time to ask ourselves that whether we have the high moral and ethical standards to do what we intend to do. So for instance, there was this big fraud research conducted a couple of years back in a laboratory in Japan, where actually the team of researchers, they claimed that they have made potent stem cells from normal cells, and it was a big thing, right? That was published in Nature, but the paper had to be retracted because the scientists themselves, they could not do that experiment again. They could not replicate the results. So if all you need to do is open up the web browser for Retract Watch, and you can actually see how this concept of retraction actually is such a big deal. So having very high moral and ethical standards are what we should look for. In a lot of laboratories here and elsewhere, when we start doing research, you have to go through ethical training. It's now a must. So for instance, if we are doing any kind of research that involves human subjects, you're doing some research that involves animals, you really need to go through a very standardized ethical training services or portal, if you will. So you're trained in that, and that is very important. Now, setbacks, very important. Now, some setbacks are amazing learning opportunities for us, and we take that. So for instance, when I was in US, I just couldn't get into any science field with a young child. So I was like, do I give it up, or do I look this as a new opportunity to pursue something that still links me with science? Because I was so passionate about being a scientist. So, and you will have your own stories, I'm sure. But definitely looking at setbacks as not something to sit back and be stressed out about, but getting excited because the setbacks are happening to give you new opportunities and challenges. And of course, crowdsourcing ideas. So having leadership values also means that you value others' opinions as much as you value yours. You reach out to your peers, your seniors, people who are in the field doing the kind of work that you're interested in. And that brings back the focus into what you're doing and how that is sometimes, and it leads to very satisfying collaborative research later on. So having those ideas and having those ideas from people that are out there who have actually done that. So sometimes just letting your ideas crowdsource, that's a great idea. So these are some of the ways in which you can acquire leadership skills. Of course, there are others out there, and my research definitely looks at the cultural aspect of it, but definitely that's for another day. But think about the ways in which you can actually talk about leadership resilience in your own careers and think how that is as important as your domain knowledge. So seek out any opportunities that you get, both online and by reading about these concepts and how it kind of, you can practice that in your own lives. It's very important to do that. So I'm going to quickly move on. At this point, I was thinking of probably doing the Q&A, but I just had some additional notes. I would like to just go with you really fast because I just had 40 minutes and I was thinking I'm just going to spend some time discussing questions with you. So the additional notes are this, that first of all, do have a very good and updated CV and keep it in Google Docs where you can work on it every day. You have to use social media as a resource. Think about the ways in which you can build meaningful relationships with others. So it also means that, building networks, having collaborative ideas, liking someone's work, talking about somebody's work, thinking of what your story is going to be. So for instance, in any competitive field, when you're thinking of applying, what's your story? Why would the organization hire you? Or what's your research? Why is it so interesting? Or why do you deserve to be hired? So something like that in your own mind, and then craft your identity on the basis of that. So please make sure that you are having a very good presence in the social media. Sometimes we don't do that. So these days, let me be very honest with you, that digital presence is very important. Most of the time, ATS, and this is called the applicant tracking system, because good organizations get a lot of applications. It's very important for them to know who you are. So if you are on the internet, you're searchable, there is some information about you, it's always helpful. So please search your name in the internet, and if you are not showing up, make sure that you have material. Please get a LinkedIn account. It's very important to liaise with like-minded people with whom you're thinking of, researching or sharing or learning about their work. Make sure you have a picture in that LinkedIn account. So making that active is a priority. Getting through to people, knowing people, and definitely using word clouds. Now, what are word clouds? If you know, in the internet, it's a huge thing, right? It's beyond you and me. So having strategic words actually helps people to find you, and you also find others. So for instance, if nanotechnology is what you're interested in, having that word or similar words around nanotechnology, that can get you the information that you're actually looking for. So some of these can actually help you to craft a better career, right? Your own persona. You can reach out to people. It gives a definite advantage in your career for sure. And by now, I'm sure you will agree with me that just having the expertise or domain knowledge, it is not enough. You really need to practice resilience and leadership, something that is not traditionally taught in school or colleges or universities, something that you need to learn on your own and be the best in what you do. So with that, I would like to wish you all the best in what you do. I'm so excited that we had this opportunity to interact, and I'm sure we're going to have more. I would like to thank you for your time. I did have a slide about the thank you one. Show you that, yes. So there it is. So thank you so much. And I would love to hear your thoughts and your ideas and whether this session was useful to you. Or what do you think? Just going to move this, and I'm really, I'll go back to my chat box, and I'm really excited about it. So you see my chat box. Yes. Aha.
Yeah, you can check the chat box, Lina. I mean, Dr. Datta. You can find a lot of comments about your, really fantastic, wonderful.
Thank you. Thank you. Any questions, guys?
Yeah, participants, please, you can ask questions.
Have a conversation with me, and thank you. Some wonderful, wonderful comments. Please, I'm just going through them, and thank you. Thank you for, saying yes to my questions. I really appreciate it. Thank you, Dr. Farooqui. Really happy to hear. Yes, steadfastness. Thanks, Monica. Really appreciate that. Thank you, Komu Yadagiriji. Thank you so much. Really appreciate it.
Yeah, there will be announcement about the participation certificates. So participants, don't leave the, there will be a, link sent to you. So you have to fill the details. So you'll be receiving the e-certificates. Yeah, you can interact with, Dr. Datta. Let me post.
Guys, any questions? I'd love to have some questions, or any that you feel that we can always discuss this. I'd love to have the topics that we talked about. And I think it's thank you, Dr. Farooqui, Prof. Farooqui. Thank you for that wonderful note. I really appreciate it. And I did have, yes, thank you. And yes, about the ethics and morals, definitely. And I personally think that we just don't do it now. There is not enough work. We talk about that. We discuss about that just as something from the lessons. I remember my training as a botanist. I was never, ever taught about ethics and morality, something that, makes a lot of difference to what we do. Thank you so much, Pujita. Really appreciate it. Any questions for me? Anything that you'd want to know more?
Yeah. Yeah, you can, sorry, interruption, Dr. Datta. Yeah,
Sorry.
participants, please fill your details. I just posted the link. You can fill the details and you'll be receiving the e-certificate. Before that, I'm going to, say, is there any question, please? You can interact with Datta, Dr. Datta.
Guys, feel free. It's okay.
Just you can
Yes.
interact. We have enough time, guys.
Yeah. That's what I was like. I want to finish early because I really have to have this chat with you. But honestly, if I ask you questions, would you be able to answer me? Like, do you feel sometimes, institutionally, that there's a lot that we can do for better mentoring? I think that is one thing I didn't discuss because I wanted to have this discussion one-on-one. One thing I really missed out was mentoring. I think we just cannot have enough of it, and that way, I'm really glad that Dr. Parvat is doing such amazing job of thinking about you guys. I think he's put a lot of thought into how he wants the webinars to be. So definitely not having me teach physics was a great idea, but actually having the other side of being a scientist or a researcher, I think it's amazing. So please feel free to discuss with me that, do you think that you have enough mentoring opportunities? Would you like to have more? What do you think of mentoring? That's a big part of your training as a scientist or researcher. How you're mentored, like, do people tell you things positively, or do you think that there's definitely a negative connotation, that it's so competitive that in some ways it's really stifling because you just do not get those opportunities to identify what your skills are because you're constantly criticized? And I think one thing that happened to me was also it's always about what we do wrong. It's never about, what is it about us that's good? Like, what are the strengths and what are opportunities? I think that is something that we can definitely improve upon. The ways in which we do current mentoring to students. What do you think, Dr. Parvat? No one's talking to me, so you have to talk to me.
Yeah, I mean, doesn't anyone want to talk to the Dr. Datta? If you don't have any questions, so yeah, let me propose the vote of thanks to the Dr. Datta. Any questions, please?
Anything on YouTube? I was just curious. I can't see that.
Yeah, okay. Yeah. Let me, it's my privilege and pleasure out of thanks to the Dr. Datta. Dr. Datta talked on a pathway to career and research. It was really wonderful, Datta. You have given really excellent information regarding the, the motivation towards the research. You have also talked about enormous information regarding the motivation and research with the awesome examples. So you also, elaborated very well a role of communication, leadership, resilience in crafting a robust research career. I mean, I really, I did know before that, but, you have given really wonderful information regarding the resilience, like, identifying the real challenges, community resources, family resources. And also you have talked about, you have spent a lot of time, really, it was really wonderful leadership. Leadership play very important role in, in our day-to-day life or research and technology. Like when you're guiding the, students, it play very important role. I mean, giving the training, the best training for the student, it is also play very important role. You have talked about the STEM or structural training, which is very important for a faculty members and which would help a lot to train up the student to make them good scientists in the future. You also talked about in order to successful any person in their career, in their profession, one should have a good leadership skills. That is very important. I guess we have to improve that skill. I mean, you have explained wonderful with examples and publications, articles. And you have also talked about how do we acquire leadership skills. I mean, that was really wonderful article, and like high moral values, ethical values, new challenge, like, opportunities, all this stuff we have to be, especially we have to improve our leadership skills that would enrich us to successful in our academic. So thank you so much, Dr. Debalina Datta. I mean, you have given wonderful information, and the participants really, they were like, very, I would say, interactive. They were posting the messages, awesome message, like, everything is like, very interactive. Thank you so much. Thank you for accepting this webinar. I hope the participants would have enhanced, receive the knowledge in this direction. Thank you, Dr. Datta.
Thank you so much.
You can stay a little more. I mean, I have a concluding points now for the for this webinar. Let me complete that, then we can leave the. I mean, before that, I think everybody please fill the form, and you can receive the e-certificate to your email ID. Please fill it. And before that, concluding point about this, one day international webinar. The main purpose of this webinar is to motivate the student towards the research and create an innovative idea among them. That's very important, and that is we are lacking actually. So as we all know that in India especially, we are lacking the research skills in the students, and we have to motivate the student towards the research, and we have to ask every student to at least think, I mean, what is the problem you are facing? At least we have to provide atmosphere to think about a problem or to think about any research small object, so that they can explore in that direction. That's a very important skill. And also the main importance we have to, it is also very important to enrich ourselves in technology and teach that to our student about the nanotechnology applications in various fields such as flexible electronics, solar cells, thermoelectric cells, bio-nanotechnology in cancer treatment, and many other smart nanotechnology applications. I sincerely appreciate to all the participants for your attention today, this morning. And finally, and that brings to the end, I would like to thanks to the first speaker. It was actually my lab mate where I was doing my PhD. It was a really great time to talk to him. And I would like to thanks to Dr. Nihar Pradhan for giving wonderful research presentation on optoelectronics in flatland, emerging device application on 2D semiconductor. I would also thanks to Dr. Debelina Datta for giving excellent talk on interactive manner, on a dialogue on leadership, a pathway to career and research agility. I would like to thanks to our honorable chief guest, Dr. Sri Naveen Mittal, IAS sir, for providing opportunity to conduct the international webinar. I would also like to thanks to our guest of honors, JD Joint Director, Dr. G. Yadagiri sir, RJD, Dr. DSR Rajendra Singh sir, and AGO Dr. Ganesham sir for accepting our request. I would also thanks to Dr. Dr. Kanchalata Madam and Dr. Thirumal Reddy sir for helping and organizing this webinar for successful completion. Finally, I would like to thanks to our principals, B. Srinivas Reddy sir, and I'd like to thank to principal of Indra Priyadarshini GDC Nampalli. So thank you one and all. It was, you guys made us like so happy. Thank you all the speakers. Thank you all the participants. Really wonderful session. I feel so happy. Thank you, Dr. Datta, for accepting this invitation. Thank you one and all. Yeah, but before leaving everybody, please get your e-certificate. Please fill your details. So please fill, is there any issues regarding e-certificates? Please let me know. I can fix that. Can anyone, give your response, please, in chat box? Did you receive it? Can I post again? Naveen sir, can you post it? I already posted, I guess. If anyone have a difficulty, I can post again. I just posted again. Dr. Kanchalata Madam, do you want to speak anything?
No, sir.
Yeah.
Thank you,
Please.
sir. Thank you, sir. A good conclusion to our webinar, successful completion. And Datta madam also explained awesome explanation of leadership qualities. Our sacred book Bhagavad Gita also tells us whatever you told in your session, that are all the qualities included in our Bhagavad Gita, madam. Thank you, madam.
Really wonderful, madam. Dr. Datta, you have given, like it was like, very interactive. I mean, very good information. That is very, I mean, it is very essential for everybody actually to develop the leadership skills. Thank you so much. Yeah, I think most of the participants are saying that they have received the e-certificate. If you have any difficulty, definitely you will receive the e-certificate even later also. There is a limit actually 100 participants e-certificate. The remaining e-certificate will be sent tomorrow. Okay. I guess yeah, I think if you don't have anything to say, I would end the session for the international webinar for today. So I guess yeah, thank you one and all. Yeah, we can close. Thank you, sir. Farooq sir, thank you so much. Overlapping question in e-certificate form. Farooq sir was saying that there is a Naveen sir, can you see that? Is there any overlapping? Naveen sir? There is a overlap. Sir was saying that there is a overlapping question in e-certificate form. Sir, Farooq sir, would you please tell me what is the overlap? You can speak, sir. Farooq sir. Dr. Farooq sir. Okay. Yeah, I'll check it actually. Yeah, is it? Oh, yeah. Yes, Dr. Farooq is right. Okay. What is the Krishna sir? What is that? Please unmute. Yeah, I'll unmute. Yeah, please. Yeah, you can speak actually, and sure. Okay. Farooq sir. Oh, Naveen sir, please. Yeah, you can unmute. Naveen sir. Kanchalada madam.
Just now I called to Naveen sir.
Yeah,
Naveen
I
sir,
gave host to him actually. So
checking ma'am. Naveen.
Hello.
Naveen is in Katwa.
Hello.
Naveen sir.
Hello. Is it audible?
Yeah.
Yeah, I'm checking, sir.
Yeah, there is a overlap in the e-certificate. Would you please check it? And I cannot access. I mean, would you please give the access to Dr. Farooqi sir? Or you can unmute. I mean, I think you can unmute everybody. I mean, we have only 53.
Yeah, I'm unmuting also.
So that they can speak.
Yeah, already.
At least we'll take the feedback from the few speakers.
Yeah, I already unmuted.
Few attendees, yes.
Yeah. You can unmute and you can.
Yeah, sir, Farooq sir, yeah, all the participants, please speak your feedback and directly. You can give your valuable words, which are very important for us to conduct the future webinars. Farooq sir.
Good morning, sir. Good morning, sir. This is Dr. Farooq, sir.
Yeah, good morning, sir.
Am I audible, sir?
Yeah, yes, sir, yes, sir.
Yes, sir. It was a very wonderful webinar, sir. I would like to congratulate all the organizers for this wonderful program, sir. Actually, I was a strong supporter of core domain knowledge only. But after hearing Deblina Datta madam, I have to shift my focus that only core domain knowledge is not the final thing. We need to have resilience, and we need to have a lot of good leadership skills, and also we need to have good mentoring also, sir. I fully agree with Deblina Datta madam, and it was just a wonderful learning curve for me in spite of having almost 20 years of research experience. Now I came to know that we need to have resilience and leadership also. Thank you very much, madam, and I'd like to thank the organizers also. So there's one message I put that there is an overlapping of questions in the form. that designation and your place of work, the question is there, but the answers are different. And for place
Oh,
of work, yes, sir. So that only that thing. Sir.
yeah, yeah. Naveen sir,
For
can you please fix that?
designation and the nature of your the lecture questions and the answers are not matching, sir. That's the only
But the
thing.
certificate is fine, right? Is there any issue with the certificate, sir?
No, sir, I have not seen the certificate because I just got confused with the question and the responses to that, sir.
Okay. Yeah, I think the certificate we have received it, but I didn't see any mistakes. But I think, yeah, the questions maybe I have to check it.
Yes, sir.
Yeah,
Okay.
thank you, sir. Thank you, sir. Thank you.
Thank you very much, sir, for a wonderful webinar. And I'd like to personally thank Dr. Parvatalu, sir, my colleague
It's pleasure, sir.
from
Thank you
GDC
so much.
Hayat Nagar, sir. Thank you very much, sir. Thank you. All the best, sir,
Made
for all
us
your future endeavors.
sir. Definitely we'll work, better in future webinars. Thank you so much, sir. Yeah. Would you please speak any other, other participants too? Maybe, I would see faculty members here, my colleagues, please. Krishna sir, would you please add your comments or maybe any feedback?
Yes, sir. Good afternoon to all of you. First of all, congratulations to the Department of Physics of Government Degree College, Hayatnagar, and Indira Priyadarshini Government Degree College, Nampally, for hosting this wonderful webinar. It was truly an enriching experience to attend this webinar. Clearly making my observations very clear regarding Dr. Datta's presentation. In fact, I was impressed with the presentations of all the resource persons, but particularly impressed with Dr. Datta's presentation, because that connected to the research aspect of the students and even the faculty members. I think there is definitely an approach that we have to develop for ourselves with regards to the faculty research and the student research. When it comes to mentoring, it's entirely different perspective that we have to develop with regards to the student mentoring, sir.
Yes.
So I was particularly impressed with that particular aspect of Dr. Datta's observation that she has made. And I think surely she'll be of a great resource to all of us, to our institution also. And I specifically congratulate the Department of Physics for organizing this webinar at the time of the institution going for NAAC accreditation. As an IQAC coordinator, as a quality assurance coordinator, I thank you for taking this initiative, sir, for organizing this program.
Thank you, sir.
With regards to the form, with regards to the Google form that has been done, sir, yesterday it was all right, but I think today when it has been posted in the group, there is a certain overlapping, as Dr. Imtiazuddin Farooqi said.
I don't know, sir.
And I think that can be fixed.
I don't know, but yeah.
That can be fixed. That can be fixed, and it can be set. All right, sir.
Okay, sir.
First of all, ultimately, I would like to thank each one of the organizers for arranging such a wonderful webinar. Thank you so much.
Thank you, Krishna sir. Thank you so much. Your comments made us so great. Datta, she was talking about completely really wonderful. That's a general talk. I asked her to talk about this leadership, and this is really wonderful for everybody. We have to improve that leadership skills, which helps a lot for us. Enrich in academic, especially. Thank you so much, Datta. You are getting wonderful comments from the participants. Thank you, sir. Krishna sir. Anybody wants to speak, please? If anyone add comments, please. Or else, yeah. Any questions? Any feedback? Anything? Or Venkateshwar Rao sir, Jayada madam. So anybody, Rakesh sir, you can.
Hello.
Madam. Dr. Jayada madam.
Sir, I would like to personally thank you for your presentation and also Datta ma'am's presentation.
Thank you.
It's a very thought-provoking session, sir.
Yes, ma'am.
And we hope that you will all involved in this seminar. Thank you.
Thank you, madam. Thank you. Thank you so much, madam. Thank you so much. Yeah, I guess, yeah, it's time to, yeah, I mean, if anyone want to talk, it's fine. But yeah, madam, thank you so much, madam, for your comments.
Parvatal sir.
Yeah, sir. Rakesh, sir. Sir, Rakesh, sir.
Sir, Parvatal sir.
Yeah, Dr. Rakesh Bhavan, sir. Please.
అది ఇందిరా ప్రియదర్శిని ప్రభుత్వ.
Yes, sir.
సార్ వినిపిస్తుందా?
Yeah, వినిపిస్తుంది సార్.
ఇందిరా ప్రభుత్వ సార్ ఐపీజీడిసి కాలేజు మరియు ప్రభుత్వ డిగ్రీ కళాశాల హైతనగర్ ఈ రెండు కళాశాలలు కూడా ఏంటంటే కన్వీనర్ కో కన్వీనర్ గా ఇద్దరు కూడా చక్కటి సమన్వయం సహకారం కూడా జరిగింది. అదే విధంగా ఇక్కడకు వచ్చి విచ్చేసినటువంటి వక్తలు కూడా చక్కగా అంటే అర్థవంతమైనటువంటి ఉదాహరణలతో ఈ వెబినార్ ను అర్థవంతం చేశారు నిజంగా. సో వన్స్ అగైన్ డిగ్రీ కళాశాల స్టాఫ్ క్లబ్ తరఫున సెక్రటరీగా ఈ సదస్సు నిర్వాహకులకు మీకు అదే విధంగా కాంచన్లత మేడం గారికి కూడా హృదయపూర్వకమైనటువంటి అభినందన తెలియజేస్తున్నాను. రాబోయే కాలంలో సార్.
థ్యాంక్ యూ రాకేష్ సార్. థ్యాంక్ యూ సో మచ్.
ధన్యవాదాలు రాకేష్ సార్.
సార్ మేడం కంగ్రాచులేషన్స్ మేడం.
థ్యాంక్ యూ సార్.
Yeah. Okay. Thank you to all faculty member, my dear colleagues, students, speakers, organizers. Thank you to all, one and all. It was a really wonderful day for me, especially. I was so accelerated towards my path, what I want to do. Definitely the words that you gave, that the feedback that you gave, definitely will improve and we'll follow the our successful direction in our academic. Thank you so much, sir. Thank you so much. Thank you to all. Yeah. I think Kanchanlata madam, can we close it session?
Okay, sir.
Yeah, participants, please leave the. I think it's over. The session is over. Session is completed. Thank you. Thank you, one and all. Naveen sir. Datta madam, Dr. Datta madam, thank you so much. Good night. It's too late for you, I guess. It's already 8 o'clock, I guess. 9 o'clock. It's a dinner time for you. Yeah, have a wonderful evening. Thank you so much.
Thank you so much.
Talk to you soon.
Thank you, ma'am.
Right.
Thank you so much.
Right. Thank you so much. Naveen sir. Thank you to all my dear colleagues, Venkateshwar Rao sir, Farooq sir. So all the faculty members from JDC and affiliated college, the faculty from all affiliated colleges from the Osmania University. All the physics faculty members, thank you so much.
Hello sir.
Sir, Naveen sir.
Sir, tell me.
Yeah, I think live, can we stop live in YouTube now?
మీరు డైరెక్ట్ గా అంటే మీ హోస్ట్ నాకు ఇవ్వండి, నేను లైవ్ స్టాప్ చేస్తాను.
Yeah, or can I have this? Okay, I'll just give that.
Yeah.
What are the chat box?
అంటే లైవ్ స్టాప్ చేయకపోయినా ఆటోమేటిక్గా అయిపోతుంది సార్. మనం ఎండ్ మీటింగ్ కొట్టేస్తే ఆటోమేటిక్గా అది కూడా స్టాప్ అయిపోతుంది.
అది కూడా స్టాప్ అయిపోతుంది. కంప్లీట్ చేద్దాం మరి.
కంప్లీట్ చేసేద్దాం సార్.
ఓకే సార్.
ఎండ్ మీటింగ్ కొట్టేసాను సార్, సరిపోతుంది.
Right. Leave meeting, yes.
End meeting, not leave, sir. End meeting.
End meeting, yes.
Thank you, sir. Parvatal sir.
Thank you, madam. Thank you, Tirupal Reddy sir, everybody. Thank you, Naveen sir. Really wonderful. Thank you so much.
Thank you, sir. మీకు వేరే దాంట్లో ఉంది సార్, పర్వతాలు సార్. ఇంకో దీంట్లో దానికి ఇచ్చాను సార్ హోస్ట్. దాంట్లో ఉంది సార్ హోస్ట్, అది. దాంట్లో ఎండ్ మీటింగ్ కొట్టేయండి, సరిపోతుంది.
I cannot find that.
Yes, that's it.
Okay, end